the recording. Right. Okay, I think we can start.
Good. So I'm sharing my screen. So, okay. So first, who am I? For those who don't know me, I'm a PhD student at Polytechnic. I'm in my last year of PhD. I'm doing my PhD on car dependency and car ownership modeling mainly. And I happen to be, I stumbled upon this method called gradient boosting machine about a year ago, and we've decided to use it to answer some of our research questions. And I can't say I became an expert in the method, but I definitely learned a lot by reading so much about it and learning how to apply it using R. So the goal of today is to kind of share you some of that knowledge so you can use the method for your own research question in transportation or anything else, because I do think there's many. We've discussed this with Owen. It was actually Owen's idea to have this workshop. We do think there are many applications to this method in transportation research. And so we really thought it would be very interesting for you to learn how to use it, learn the finicky details of using this method. And so here we are today. Hopefully you'll like this. As I said, it's the first time I'm giving this kind of workshop. And it's virtual. I would have done it very differently if we had been all together in a classroom. I think I would have given you exercise to do and we could practice and stuff, but that's not necessarily going to be the case today. So basically, how is that going to go? I'm going to explain what is gradient boosting in theory, how does it work, why should we use it, what are its advantages and disadvantages, what can it do, what can not it do, what can't it do, how do we analyze the results of gradient boosting? And then we're going to go into some more practical examples. So the first part is going to be taking place in this very setting of a PowerPoint presentation, so very classical. I'll share the PowerPoint presentation with all of you, of course, afterwards, and also with everyone that won't be able to stay for the whole workshop, or pretty much anyone at Polytechnic that wants to have it. And then we're going to go and see how we can implement gradient boosting in R. I'm sorry if some of you are more like Python users. I do not know anything about Python. I've never coded in Python. I've tried 3 years back, but I decided to stick with R. Maybe you're going to tell me Python is better. Maybe it is. I don't know. The point is, the examples I'm going to show you are done on R, but many of the packages that are used on R to do gradient boosting are also available as libraries in Python. And there's probably even more documentation online on how to do this in Python, but still you'll get the general idea of the process and how to do it. And I've also included many very good references on the topic, so you can dig for yourself and ask questions. Not ask questions because I won't be able to answer the coding questions in Python, but still, it should give you a pretty good idea of how to do it in Python, even though the coding is slightly different. So the examples we're going to see are example with transportation data. My idea is that it would have been great if I would have had enough time to share with you all the data up front, so you can kind of do it yourself at the end of this workshop. It did not happen. Well, I have one data set we could use, so we'll see how that goes a bit later. But in the meantime, I'll kind of show the example on screen, and after the workshop later today or tomorrow, I'll share my entire R code, the data sets that I've used, or variant of the data set. You'll see what I'm talking about later, that I've used for doing this example, these examples, so you can practice and even test other research questions that are ones that I'll be presenting. And then finally, some application and reference, example of application of gradient boosting in transportation research, and general references, very good references on gradient boosting in general, for you to dig more into this, or to cite if you use in your papers, if you decide to use this method. Oh wait, so first question, it's me asking you questions. Where do we stand right now? So a few questions to help me navigate this workshop. What is your level of familiarity with machine learning methods? I know some of you have been using machine learning. I don't know how much, maybe some of you are even more expert than I am in machine learning. I can't pretend to be an expert in machine learning. I'm only a semi expert maybe in gradient boosting. So who here, let me ask the question in reverse. Who here has never used machine learning methods?
I don't know.
Owen?
Do you want it to vote or how?
Yeah,
we
you
gonna
guys can raise your hand,
yeah.
so it gives me an idea. Let me show more people on my screen.
I see my students using it.
Yeah, so you have an idea of how it works.
Yeah,
Okay, good.
yeah. I know the principles behind it, but I have not myself ever done it. So I'm happy to
Okay.
learn.
Okay, second question. Now it's going to be as it is. Has anyone here ever used gradient boosting models? Who's used?
I think no. I think the easier has anyone used it? Yeah.
Well, who's doing the cat boost in our EV paper, Owen? Is it
Oh,
Hamid?
but that's Hamid. Yeah, he's not here because
Okay, he's not here.
he uses a lot of he uses machine learning.
Yeah,
A lot, yeah.
because cat boost is another variant of gradient boosting.
Yeah.
I've never used this specific one, but I do think it's pretty much it's very similar.
Yeah. He was explaining the differences. Like it's like a variant.
Yeah,
it's
in the same.
It's the Omicron of the gradient boosting.
It's in the same family of gradient boost of machine learning methods.
Yeah, exactly. Yeah.
Okay, and finally, and this is going to help me to know how much detail should I go to. Who's using R and who's not using R? That's my third and final question before we get started. So by raising your hand, who is using R and knows how to code in R? Okay. Perfect. So I would guess that the rest are using other packages or very débutants, beginners in R.
Yeah.
It's fine. It's all right. You'll in the end, if you want to use this, I mean, I learned many things in R just by reading and watching tutorials about things that I wanted to do. Just learning for learning. I'm not the kind to do that. I kind of learned to do an objective, and that's how I learned new ways to do things in R. And R is, there's so many ways to do one thing in R that sometimes it can be very confusing, and you end up, even as of today, I keep learning new ways of doing things that are more optimized and allows me to present my results in a better way, for example. All right, let's dive into it. GBM in theory. So what is gradient boosting? So it's a very popular and powerful and easy to use supervised machine learning method. If maybe some of you are aware of something called random forest, which is it may be more common machine learning method. So when, like, the way there's kind of two supervised learning method. There's two types of supervised learning method. There's a single strong model method where you have like a regression, a one neural network, or one decision tree, or something called support vector machine, which I don't even know what it is. And there's the other way of doing this through what we call ensemble methods. In ensemble methods, we have two methods of ensemble. First is bagging, like random forest, and the second is boosting. So random forest works by building an ensemble of deep independent decision trees where the prediction is averaged over the entire ensemble. GBM is slightly different. It works by building an ensemble of shallow, weak, successive decision trees where each tree learns from the previous tree in the ensemble. I'll explain this a bit later in the next slides. GBM, it's a non-parametric supervised machine learning method. So it can be very useful to build a model wherein we have a priori no idea of the relationship between potential predictors and the outcome variables we're trying to predict. And because it's non-parametric, it does not require very strong assumptions on the distributions of variables. It does not require assumptions either on the distribution of predictors. As many machine learning methods, this is very convenient when the data that we have is all over the place. All right, so disclaimer. Today, my goal is not to present to you all the mathematics behind GBM decision trees. For you, for this, I refer to you to the books and papers that have been written about this. They're going to be much better than me at explaining what's the mathematics behind. I'll try to explain, to summarize it for everyone to understand, because I don't know everybody's level in maths. Some of you are probably much better than I am anyways. So I didn't want to get into this. So the idea is to get to understand how it works. But if you want to go deeper, as I said, I'll have the reference at the end where you can learn a bit more about the equations behind the different algorithms. So a brief history of gradient boosting. Well, first, what does GBM mean? Well, I realize that there's two ways. It could mean gradient boosting machine or gradient boosted model. It abbreviates the same thing, GBM. It's pretty much the same thing. As you can see, this Friedman guy, which is called Jerome, same as me. Jerome Friedman is the one who came up with the gradient boosting algorithm in the first place. He also wrote a book with two other distinguished professors. And as you can see, it's different names for the same thing, but it's all the same. It's the family of boosting methods. So the origin of boostings comes from the idea of combining weak learners models sequentially, where each weak learner kind of focused on the observations that were misclassified by the ensemble, so all the weak learners before, in order to learn what it didn't manage to learn up to this point. That's how AdaBoost, which was kind of the first successful boosting algorithm, works. AdaBoost works by weighting the observations, putting more weight on difficult to classify instances and less on those that are already handled well. New weak learners are added sequentially that focus their training on the more difficult patterns. So as the tree growing process, the idea is really to focus on what those observations that are harder to predict. And the predictions are then made by a majority vote of the weak learners' prediction, weighting by their individual accuracy. As I said, this is the most successful attempt at this was something called AdaBoost, which was invented in the 80s and 90s. I can't remember. And in AdaBoost, the weak learner model is a very simple single split decision tree, which is called a stump. So that's maybe why it was a bit more limited. The idea was that Friedman was the one that generalized the boosting algorithm, so it could use the principle of gradient descent and thus can be applied to any loss function and can be used for other things than simply binomial classification, because AdaBoost originally was only for binomial classification. All right, so that's it for the history of this. Why should we use this? That's the main question. So what are the advantages of gradient boosting? First, it has very high and very hard to beat accuracy in the things that I've read, but maybe because people are preaching for their own methods. But in the reference that I've read, people say that it has higher accuracy than things like random forest or most other machine learning methods. It offers very high flexibility because it can optimize on many different loss functions. And it also has many hyperparameters that can allow us to tune the algorithm to increase even further its predictive ability.
Jérôme, hold on.
Yes.
Maybe just explain a little, because I remember the first time I saw a hyperparameter and the whole idea of tuning. It wasn't clear to me as somebody who didn't know about machine learning what that was.
I've got a slide coming up for that.
Oh, you do? So, perfect. Okay.
Yes.
Excellent.
So it's going to be explained. Most of the things I'll say are going to be repeated throughout the workshop and throughout the examples that I'll be presenting. So other things that you to consider, as you've probably read on the screen by now, it does not require much data pre-processing. In some examples that I've seen online, people just take their entire data set, jump this, run this into an gradient boosting algorithm and see what comes out of it. In truth, if you're to write an article with the method, you should do a bit more data processing, that's for sure, because it can improve further the strength of the model. And also, it's very good for handling missing data, as long as there's no missing data in the outcome variable, in the variable that you're trying to predict. But there can be missing data in the predictors, and it doesn't matter, it's going to work anyways. Some of the disadvantage is that there's a kind of a high risk of overfitting, but there are many methods to overcome that. It can be very intensive, to be honest. Depending on the strength of your machine and the computing power of your machine, it can take a long time, depending on the number of observations that you have and the number of trees or iterations that you're going to do to achieve your model. We're talking of several minutes per model easily, but it can go up to even more than that. As I said, many tunable parameters, but this required kind of a lot of fine-tuning to find the right hyperparameters, and I'll explain what hyperparameters are in a couple of slides. And finally, one important and disadvantage of the approach is that, unlike regression, either be it logistic regression or linear regression, the method cannot test if a variable is a significant predictor in a model. It gives us something we call relevance, relative influence of the independent variables that we included, but it does not tell us if those variables are statistically significant in the model or not. It only gives us an indication compared to the other variables that are included in the model. You'll see a bit later.
I think Bobin possibly has a question.
Yes. Hi, Bobin. Yeah, I forget to mention, do not hesitate to interrupt me.
Yeah, it's hard to see the hands. Yeah,
exactly.
Yeah.
So Owen, you're in charge.
I'll watch for that. Yeah.
Sorry to disturb you. So could you please give more important information for what the meaning of boosting? So because for the name is very I'm not familiar with the meaning of boosting or the bagging or something. So what yeah, and could you please give more explanation for that?
Yes, you are asking the question at the very perfect time, because this is exactly the slide that explains it. So boosting methods aim to add each new base learner model, and most of the time base learner models are simple decision trees, to the ensemble of existing models sequentially, where each new model is trained by taking into account the error of the entire ensemble up to this point. All right. What does that mean? We start with one tree. Our tree can have, let's say our tree has like 3 splits. So it's a single decision tree with 3 splits. It gives us a certain level of prediction of our outcome variable. It's far from perfect. We add a second tree to that. The second tree learn from the mistake of the first tree by learning of the residual, by taking into account the residual of the first tree, and then by learning on the first tree, it can improve the model up to this point, and so on up to thousands of trees. This is how it works. This is the general way the algorithm works. So it's pretty much what I just explained. We fit the first decision tree, we fit the next decision tree to the residual of the previous all the previous decision trees, and then we add the new tree to our algorithm, and we fit this new tree to the residual of everything we had up to this point, and so on and so on. So it's called boosting. It's a stage-wise additive model of a certain number of decision trees. It could be other weak learner models, but today we'll focus on decision trees. So that's how it works conceptually. If you want to see more of the mathematics behind this, you can read Friedman's paper. I have the references at the end, but that's how it works. So I don't know how well this was explained. I don't know if you have, again, as Owen said, dumb questions are not dumb. They're only questions that other people are too afraid to ask. So was that clear so far?
I have a question, Jerome. I think it's a really basic question because I haven't worked with machine learning process, but what is exactly a decision tree?
Okay, very good question again. This whole slide was based on the idea that people know what a decision tree is. So a decision tree is, I should have included a slide about this, but a decision tree. So you can picture a tree. A decision tree is made of several splits. So a tree with one split means you take your predictor variable. Let's say it's a binary variable. Let's say it's gender. Okay, well, gender is not necessarily binary, but so it's a bad example. But we're going to use it anyway. Let's say female and male. Let's say that your variable that you're trying to predict is the number of trips that people are making in the day. What we know is that women tend to make more trips than men in general. And so your decision tree, if your only predictor is your gender, your decision tree will be 0, it's a man, 1, it's a woman. And if it's 1, then it's going to give us a higher value for our outcome variable, which in this very overall example is the number of trips per day, for example. And then we can add other variables. Okay, if it's a woman, if she's below between 18 and 30 years old, she's making even more trips. And so the second branch of our tree is the age, and the third branch of our tree, the second split of our tree is another variable. The third split of our tree is going to be a third variable, and so on, up to the point where you build a tree. And depending on the path that you take on your tree, you're gonna end up with a certain value of your possible value of your outcome variable. Does that explain how it works?
Yeah, exactly. Thank you. It's like
Okay.
the dependent and independent things that we are always working in the LR model. Yes, perfect. Thanks.
There is a question from Mohammed that he wrote.
Yeah,
Mohammed,
I don't see the chat.
So
you want to read it to me, Owen?
is this optimization method stuck in local min? I'm not sure what he means by local min. As I read, is superior compared to gradient descent. Do you understand the question?
Yeah, the question is not super clear, but I understand. And there's something coming up for this.
On that, okay, perfect. Well anticipated, Jerome.
Yes. So far, the questions have been anticipated, but it's a very good question.
Sorry.
One more.
Yeah, because for the last slide, it said the new tree. So the new tree means the new level of the tree or completed a new tree.
Completely new tree, and that's where gradient boosting differs from a method which has one very large single tree. So you can, let's say you have 20 predictors in a one very large tree. You would have like 20 splits, or even more than 20 splits if you have more than one splits per variable. This would mean like a huge decision trees, and at the very top of the trees you have the probability or the expected values of your outcome variable. In gradient boosting, we use smaller trees with only a few splits in each tree, and each tree kind of learns from the trees before, so that the splits that it makes are better than the trees that were previously in that were already in the ensemble of decision trees that we have.
By looking at what it got wrong. Right?
Exactly. By looking at what it got wrong, we're able to refine our splitting of our variables, especially continuous variables. Oh, we got it wrong this time. Okay, maybe we should split it this way. And then, so we add up those trees, and that's what gives us the prediction in the end that is much better than one single big decision tree. Because it works sequentially, I've added this. I don't know how much you see it moving here. Now it's moving very slowly. The GIF image on the left is a representation of how this works out there you see. So it starts with something that is very crude, basically a line. The red line was a flat line at first, And then as we add more trees to the model, it really refines the accuracy by learning, as Owen said, of the observations that were misclassified. The prediction accuracy, this is taken from a very good book on the question. The prediction accuracy, it gives you here an example. So a single stump, it means a tree with one split, will give you a prediction accuracy. Let's say in the case of a binomial outcome variable, we're trying to predict a binomial outcome. A single stump means a single split. The single split, as I said, gender, let's say gender, male or female. This single split could improve your accuracy slightly better than random guessing. If you have a massive decision tree with, like, for example, 244 nodes, it improves your accuracy much more. But if you add many single stump trees, you can see by boosting iterations, we mean the number of trees that are added to the ensemble of trees, we can decrease the error, the test error rate, or increase the accuracy of our model by quite a bit. So that's the idea of how it works. By combining this, I know I've had a hard time at first getting my head around this, and even I am not sure I explained it very well. But hopefully it's enough for us to keep going in this presentation. And so how do we optimize? This is the next question we're going to ask. How is this red line getting ever closer to this blue line here on the left image? So it does that by the gradient descent, which is the way that the boosting algorithm of AdaBoost was generalized. It tweaked the parameters iteratively to minimize the loss function. So as we said, it focuses on the misclassified cases in order to minimize the loss function that can be optimized. And the loss function can be any different. I have a slide for that later. The loss function depends on the type of variables that is your outcome variable. So how it works is that gradient descent pretty much is you're trying to find that minimum. That minimum can be very simple. If your function is a bowl-shaped curve like this, the minimum is at the very bottom. So you want to find this by learning with very small steps. So that's why we use very small trees to make only small increments in the direction of our gradient. If steps are too small, it takes forever. If steps are too big, you might miss that minimum. Now, to the question that Mohammed asked, because he asked a very good question. What about, okay, this is very simple. It looks like in this function, there's only one minimum and it's the global minimum. But in reality, functions are much more complex than that. And there could be local minima and the global maximum. How do we optimize our chances to reaching the global maximum, the global minimum, sorry. That's where stochastic gradient boosting comes in. So again, our mathematician Jérôme Friedman updated his 2001 algorithm by including a stochastic approach to the gradient descent. And how the stochastic approach works is that it samples at every iteration. So before adding any tree to our ensemble, and so at every iteration, it fraction a random sample of our training observations. So let's say we have 100 observations. At each step where it adds a new tree, it only train on a subset of, like, let's say 80% of our observations. So only on 80 observations. What this allows us, it adds randomness to the algorithm, and it can help it jump out of local minimum to try to find the global minimum. I've included this image because I do think it kind of expresses what it is. So you don't go in a straight line straight to the bottom. You kind of zigzag your way all the way to the global minimum. Is that clear so far? Excellent. There's a question, Meredith? no, you.
Somebody's
Leave
getting
your pouce. C'est bon.
yeah.
Okay, so we get to the point where we apply this. So how does it work? We apply to run a gradient boosting algorithm. We first need to decide on the base learner function that we're going to optimize. As I said, up to this point, the most common base learner model that is used in gradient boosting is the decision tree. Decision tree are very powerful on their own, and when combined in a sequential manner, they can become very, very powerful to explain our outcome variable. But there are other options like simple linear regression could also be a base learner, and we can learn from, and the same process can be applied. Today, all the examples are going to be by using decision trees. That's how I've implemented this, and decision trees can even be used for, even if your outcome is a linear, even if your outcome is a continuous variable, you can still use decision trees to model it. And then once we choose our base learner, we choose the form of the loss function to be optimized. That's where the generalization made by Jérôme Laviolette comes in. It pretty much allows us to use any loss function that can be optimized. And the loss function depends on the type of variables that we want to predict. So you don't have to learn all this by heart. You just need to understand what kind of loss function should be applied, and in the different packages in R and the same in Python, you can choose from those functions depending on the outcome variable you're trying to predict. So it uses some typical, every loss function is associated usually with a distribution. So for a binomial outcome, for example, the loss function is based on the Bernoulli distribution. For continuous outcome, it can be placed on many different things like Gaussian distribution and so on. In short, for every variable, for every type of variable, there are usually more than one option out there that you can use. Which one to choose from? In all honesty, I'm not sure, to be honest. For example, for continuous outcome variable, how should we use, why should we use the Gaussian instead of Laplace, instead of Huber loss? I honestly don't know. Some said that you can just test it and see what works best. But it could also depend on the form of your of the distribution of your outcome variable. In all truth, I would need to read a bit more about that to know which of those would need to be selected for the same outcome variable, the same type of outcome variable. All right, which brings me to those hyperparameters. As I said, one of the flexibility of gradient boosting is that you can adjust many boosting parameters in order to optimize even more your algorithm and to try to get it to be better at predicting what you're trying to predict. So there's three categories of boosting parameters. The first is the number of trees. So we're talking about an ensemble of decision trees. The question is, how many trees should we take for our task, for our optimization process? Again, you can usually how it works is that you choose like an upper limit to the number of trees, but the idea is that, let's say, and you'll see in my example, that's what I do later. Let's say we take, okay, let's say we take 5,000 trees, but we might reach our optimal level or the minimum of our loss function way before 5,000 trees. And that's where some sort of mechanism called cross-validation are very useful, because the cross-validation allows you to decide how many trees you actually need to solve your problem.
Just
before,
yes.
Maybe
briefly explain what overfitting is, because I think that's not always clear.
I think I had the thing on the next slide.
Yeah.
Yes.
Okay.
So I'll talk about overfitting on the next slide.
Okay.
The next thing is the learning rate. The learning rate is, you remember those here, the learning rate is how fast you're going down the gradient, pretty much. So the learning rate is a number between 0 and 1, well, a fraction between 0 and 1. It can be very small, 0.0001, or it can be 0.1 simply. So these are the size of the steps you're taking in the direction in order to find your minimum. What this means is that these two things are linked, because if your learning rate is very small, it means it's gonna require more iterations to reach and to find your minimum. And so if you have a lot of processing power, you can put your learning rate very low, and it's going to go very slowly, but you're going to reach you're still going to reach your destination, and you're going to be certain that you're not going to miss your destination, and your destination is the minimum of your function. Now, so this is the general boosting hyperparameters. There are two tree-specific hyperparameters, the tree depth. So how many splits do we have in our trees? As I said before, boosting algorithms use simple decision trees. By simple decision trees, we mean decision trees with only a few splits. So the typical range is between 1 split, which is, as we call, a stump, which was used in AdaBoost, for example, or up to like 6 or up to sometimes 8 splits. What does it do? Those splits, it actually control the interaction between the predictors. Because at first split, you can use a first variable to split the probabilities based on that first variable, and then the second place you use a second variable to split the probabilities. So if you insert 0 on the first question and 1 on the second question, it's going to get you somewhere. If you insert different things, it's going to get you someplace else. So the idea is that this way you can control, there's likely interactions between your variables, because variables are often correlated, and one is only effective when another one is present. So by having a few interactions, but allowing a few interactions in your trees, meaning by having a tree depth of more than 1, you allow those interactions between those variables, and it can actually help solve certain problems, but up to a certain point. There's been many simulations and tests. If you go beyond 6 or 8 trees in gradient boosting, 6 or 8 splits in your trees in gradient boosting, it's not, you don't see much more improvements. And finally, the minimal number of observations each nodes. So at the end of your tree, how many observations should you have? If you put only 1, it means that this is only explaining things for 1 observations, which might not be very generalizable. So the idea is to have at least a few observations per nodes, so your ensemble of trees can be generalized to your test data. What did I miss? Let's see my notes here on the right that you guys don't see. I think I've said pretty much anything. Do you have any questions about that? I'll come back to those hyperparameters during the examples. You'll see how we select them. We'll see how we search and tune them to get the best solutions.
So there's a question from Vincent.
Wait.
Yes, I was wondering on the split between 1 and 6, are we talking about like a stage? Or like 6 decision, like 6 gender, if you keep on the gender example.
No, let me see if I can write something. I think
would it be like gender to having a child, to having like what age, to what type of job? Is it those types of splits, Jérôme, or?
Yes. So a split is like, I'm trying to
find an example.
I should have included a decision tree here.
Oh, you're drawing on the
I see it.
The 2 screen.
With my very nice drawing skills.
Okay, so you can have like 6 different state division.
Exactly. It's kind of division in your tree. So this is your variable 1 here. So if your variable 1 has a certain values, it could be 0. If it's a binomial variable, this could be 0, this could be 1. And then your second variable is here. In the case that you have 0 here, your second variable can help us guide our outcome and, well, help us.
Does it always split in 2, or you can split in 3? Or
exactly, it could be more than 2. It could be, this is if it's a binomial, but it could be if it's a categorical variable, you can have 1, 2, 3, 4, as many as categories that you have. This is still one split, but this can lead to much more split in the tree later on. As you can see here with my very nice drawing.
Okay, man. Thank you.
And the same for continuous variables. So as I said, decision trees are not only used with categorical predictors and categorical outcome variables. You can have a split can be a split between values of a continuous variable. Let's say a continuous variable is density, population density. So this split could be if you're less than 5,000, you go this way. If you're above 5,000, you go this way. So it could also apply to continuous variables. So that's how it works. So the idea is that trees that are not too big are performing better in general, but you can understand why trees with a few splits can work better than trees with only one split, which would be this would be what they call the stump, which is kind of limited, as I said, because there's no interaction between variables. Each tree only use one variable for the split, and that's it. While in the end, we want to use trees with at least a few variables, but not too many either. And the not too many is just based on what people have learned by testing many different things. And it happens that beyond 8 splits for gradient boosting, there's not much improvement. Unlike a single tree, you want as many splits as possible because this can really improve your model. But in gradient boosting, we don't need more than up to about 8 splits. That's what I read. Again, yes.
Sub question to Vincent's question is so I guess once you split in one direction or the other, it's not necessarily the same variable that will split after that. So if you go on the left node, like let's say we're doing variable 1 and then we have variable 2, but is variable 2 applied across all branches, or do you know if that would be the case? Do you know what I mean?
Yes.
So let's say the first variable is you have density,
like here,
right?
this second level, let's say this is our level 1. Let's take this big tree here. It's becoming a mess. Okay. Is this variable here variable 2? Is it the same as this variable 2
exactly.
here?
Do you know?
In truth,
you're not sure?
I'm not sure.
Okay.
It's a very good question.
Yeah, that's fine.
Sure.
No, it's just more of a
What I know is that, as we said, in gradient boosting, we use many trees. I know that each tree in our ensemble of trees can use different variables. So let's say we have 10 variables. The first tree only uses the first 5 variables. The second tree uses variables 2 to 7. The third tree uses variables 1, 3, and 9, 10, for example.
Yeah.
So this can be the case. Only a subset of variables can be used in each tree. And this tree depth that we specify, this hyperparameter, it's actually a maximum. Okay, so it means that in our ensemble of tree, we can have trees with only one split, but we can also have trees up to, if we decide that our maximum of split is 5, we can also have trees with up to 5 splits. But the question is, with different split, let's say 0, 1 here, are we going to the same variable here after the split on the left and on the right hand side?
Not sure.
I would think so, but I'm not sure.
Okay.
I'm uncertain.
That's fine. Yeah.
If someone has the answer to this, please provide. I'm not certain. Bobin?
Yeah, thank you. Based on your example, could you please show what the number of trees and what is the tree depths for your example? Based on this example, what you are drawing,
Yeah. Okay. So the tree depth is the number of splits. So we have 1 split, 2 splits, 3 splits. You see, even though each split can have more branches because we split, So the number of splits is the number of levels in your tree.
So here we have 3 levels, right?
1,
Yeah.
2, 3 levels. This is a tree with a tree depth of 3. Yes.
Okay. And the number of tree is 1.
The number of tree in this example on the screen, it's 1. But boosting boosting works by like creating a first tree like this, and then it compares the results. So let's say the tree grows, and then then in the end, the last thing is that it gives you a value. If you're going this path, let's say we have a binomial outcome because this is more simple. If we're going this path, you're very likely to have the outcome A. If we're going this path here, you're going to have B. If you're going this path here, you're also going to have B. If you're going this path here, you're going to have A, let's see, and so on. So this is one tree. What it does is that, oh, okay, but then it compares. Are these correct? And then you test this. Is this correct compared to the real outcome? If it's not correct, okay, maybe this split here wasn't good. So we add another tree where we split differently at this level here. Well, this whole level here, we split differently, and it gives us something different. And that something different is actually slightly better, so that we get this prediction correct this time.
Okay, so
that's how it works.
Finally, we only have 1 tree, right?
No, at the end of gradient boosting, generally you have hundreds or thousands of trees. And it's the kind of the sum of those trees gets you your final result and your final predictions.
But you said only 1 is the best.
Yeah, yes, but it's not the good point. It's not necessarily that it's the best. But the second tree you're going to grow, you grow this tree by learning from the tree number 1. And so it's the combination of those 2 trees that actually gives you your final output. So at the end, we don't only use the tree number 100. We use all the tree up to 100.
Which I guess, yeah, because it's like, I think this goes back to the difference between the ensemble method.
Yes.
Versus, yeah, because just like a simple decision tree is just that one tree that you would,
tree with
huge
many,
tree.
many
Yeah. It is. Yeah. Conceptually, I think it's hard to understand that you're taking all these like bushes and somehow you're getting this a better fit. But yeah, it's learning from those mistakes. Yeah. I was going to. I don't know if there's one more question, but do you want to? Well, it's not a bad idea to take a 5-minute break every hour, or?
Yeah, I think I'm almost done with.
The first little bit. Okay.
Yeah, the theory part, and then we can take a break before I move on to the examples. It's gonna get clearer with the examples, I think.
Yeah.
All right, so I'm gonna.
You can clear it if you want.
Clear all this thing.
Yeah.
Clear. All drawing. Okay, good. Clear this thing. Okay. Perfect. So boosting parameters, tree-specific parameters or hyperparameters, and then we have the stochastic parameters. The stochastic parameters are it's when you proceed with stochastic gradient boosting, when you add that randomness that makes sure that you don't get stuck in a local minimum. This works by like fractioning up. There's several ways to do this, but the main way is that you only take a subsample of rows before creating each tree. So as I said before, if we have 100 observations at each, depending on the values that you specify here, if it's 0.5, it means at each tree, you only use 50 of your observations to create a new tree and add this tree to our ensemble. And the next time you use another 50 different observations. Well, some of them are going to be the same, but it's at some point you only have a fraction of your entire observations that is used to grow each new tree in our ensemble of decision trees. And remember, one tree is one iteration in our process, because at each iteration, we add a new tree to our ensemble of trees. Another way is by fractioning columns, and this can be useful in some ways. The impact of subsampling columns, what does it mean to subsample columns is that, let's say we have 10 variables, then at each, and our values for this is 0.8. So it means that at each tree, we only use 8 of our 10 variables. So we exclude 2 variables. We don't use these for creating our new tree. And then the next tree, we use 8 other variables among our 10 variables. It could be the same one, it could be different. Every time it's different. And this way we subsample the columns. What does it do exactly? If there's a few, if there are fewer relevant predictors, more noisy data, let's say we have a lot of predictors, but only a few of them are relevant. It could be very good to have a high subsampling rate, meaning the value here is low, because it makes it more likely to select those features with the strongest signal without all the other irrelevant predictors. So when you're going fishing, for example, and you throw out there a lot of variables, it's likely that some of them are not relevant to our outcome variables. Some of them are. It's apparently better to subsample some columns at each tree, so we only take a subset, and sometimes you're going to fall upon a subset which only uses the relevant parameters, and this tree is going to be very good, so it's going to help your algorithm. And the last thing is you can also subsample columns before each split in each trees. This is getting a bit more complex, and I'm not sure what this adds, to be honest, to the process. It just adds even more randomness. And as everything, adding this kind of randomness can help you find things that you wouldn't find otherwise. But to be honest, I've not experienced much with this very last parameters. I've mainly focused on the first 2 parameters in my own modeling. Okay, so now to the question of overfitting. How many slides do I have left before interpretation tools? I don't know. Maybe we should take a break now, Owen. I don't know. I've got 4 slides left, but each slide has a lot of information. Let's do this one and we'll see after that.
Yeah, it sounds good.
Okay, so as you asked the question of overfitting, one problem with gradient boosting is that you can overfit. What does overfitting means is that what it does is that it reduces the generalization of the algorithm, because it leads to predicting only the training set and not the functional dependence between your predictors and your outcome variable. So if you're overfitting, because with many trees, you can go up to a point where you reduce your error rate on your training set almost down to 0. It means that your model is going to predict your training set so well that it's almost perfect. But if you apply the same model to your test set, which means a number of observations that you've left out that you haven't used in your training, then you might end up having something not so good after all, because the algorithm that you've produced has adapted very specifically to the training set that you have, but not to other observations that were different from what you found in a training set. Does that make sense? And so the idea is to avoid that. And to avoid that, there's a few regularization methods. Subsampling is one of them. By subsampling, it's one of those here. It's this one here. As I said, you subsample before creating each tree, so you're less likely to overfit your model. The second thing is by using shrinkage, a smaller value of shrinkage or learning rate. If you learn very slowly, then in the end you can overfit, but you have more times to know if you're at a point where you're overfitting or not, because it allows you to test very often if you're overfitting or not. And how do we test if we're overfitting? Well, this is where something called cross-validation comes in. Cross-validation, all right? So it's a bit complex, and I'll see it again in my example. As it's the case in many machine learning methods, a good way to do this is that you take, let's say, 70% of your sample for training and 30% of your sample for testing. The 30% for testing, you never use it to build your model. Among the 70% that you have for training, you're going to split that even more. What cross-validation does is that you select a number of cross-validation folds. Let's say our number of cross-validation fold is 5. So we split our 70% training set. We split this set in 5 different sets, which is going to be 1/5 of our 70% of our entire sample. Among those 5 subsets, one is reserved and step aside for internal validation. And the rest, the 4 other subsets, are the 4/5 of our training and training set is going to be used for fitting our model. And the test, the algorithm process by testing every time a new tree is added. It also tests on the 1/5 of our training sets that is not used for training, but only used for testing. And then the validation performance is aggregated for each of those folds, because the thing is repeated for each of the 5 by holding out each of the 5 fold, each of the 5 subset independently. So let's say we have 5 subset. The first time you take subset 1, 2, 3, 4 for training, and you reserve subset 5. The next time you take subset 2, 3, 4, 5 for training, and you reserve subset 1. And so on and so on. So your validation, your performance measure is based on this aggregation of this different way of splitting your subset and using them for training or testing. It's the first time I'm explaining this out loud. I don't have a clue of how easy that was to understand. But that's pretty much how cross-validation works. And it's cross-validation, I believe, is something that is commonly used in machine learning methods to avoid overfitting. So maybe some of you were already familiar with it. I hope this was clear. If it's not, do not hesitate to ask questions.
There's somebody, Bobin, yeah.
Bobin
Yeah.
is good with questions.
Yeah, this is good.
Yeah, so does that mean, so you only have, for each time, you will have 2 data sets. So one is for training and other is for testing, right?
Yes. So
just
you can have, okay, I should have the, let's draw again, because I think drawing is good.
Visualization of the
visualization. Actually, I mean, this workshop can definitely be improved, and one improvement is it's to make more.
Oh no, you just learn.
I'm explaining.
Yeah. This is every time you teach, and then you learn. Oh, I need a blank page here that I'm going to draw.
Okay. Let's say we set our cross validation with 3 folds. I say 3 instead of 5 because it's going to be easier to draw. So we have our training set and our testing set. Test and train.
While you're trying. So for those very new, so the training set is often your largest amount of data.
Yes.
And this is where you're trying to teach so it's learning from your training set. It's trying to develop your best prediction. And then the testing data set is going to check, is that
final step of your model is to check the accuracy on your testing set. Well, the truth is you can only do a training set and only use cross-validation, but I prefer to do it this way. So you first split your set into, a common way is 70-30. Sorry for my writing, it's terrible on this with a mouse. And you only use this for training, and this is really what you held out for testing. For testing, how good is your model in a binomial classification problem? You train your model with this, and then you predict with your model, you predict what should be the outcome values on your test set, and then you compare and you test the accuracy of your test set by saying, oh, well, my model got 65% of my outcome variable of my test set correct. Okay, where does cross-validation comes in? Well, on this training set, we can split that even more. So in the process of, this is done before running your GBM model. This is not, this is never touched by the model, by the algorithm, never. This, we only touch the training set, and the training set could be split even in more ways, which is the number of folds that you put in your cross-validation fold. So if we say our number of fold is 3, it means that we split this in 3 more sets. At each iteration of our boosting algorithm, we use 2, in a case here is k minus 1, which is 2 of our training subsets to train our new tree in the model. And we left out the third set to test if this new tree is good and add something to our entire ensemble of trees. And then at the end, and you do that, but these trees are not always the same. So sometimes at another tree, it could be, this is 1, 2, and 3. As I said before, if this is for building a second tree, you could use 2 and 3 as training and 1 as test for internal validation during your algorithm. Does that make sense?
Yeah, so 1, 2, 3 is a completed data, right?
1, 2, 3 is our
training
set.
Okay.
This original test set that we took out at first, before even running our algorithm, we just take this out. We never use it to train our model. This is always left out for pure testing. At the end, our final model with the thousands of trees that we're going to have, we're going to use it to test how good it is on our test here. This splitting here, this cross-validation splitting here, this is done during the training process to make sure that we do not overfit during the training process. Every time we only test on 2/3, well, 2/3 because I selected 3, and we train on 2/3 and we test on 1/3. That's how it works.
Okay. Okay, so when we compare the 1, 2 with 3, so or 2, 3 with 1, so what you will learn from the training data?
Well, you make sure that you do not train to your specific data in a way. So because in your subset number 3 here that you reserve for internal testing, you can have observations that are unique and that have no equivalent in 1, 2. So the idea is that a bit like here, training and testing, it's a bit like here, training and testing. You're avoiding that your model is going to be very specific to your observations, meaning that if there's an outlier here, a very strong outlier variable, observation here, that outlier is not in the test set number 3. So in the test set number 3, if this was trained with this outlier in mind, it might not be as good as predicting the test set because of this outlier. But if this was not there, if this process was not there, then in the end, our model would be very good at predicting even our outliers in the model, but these are outliers, so you shouldn't be good at predicting them. So what you end up doing without this sorts of cross-validation process is that you end up predicting your training set, but only your training set, and then your model cannot be generalized to any other data set.
Okay. So the 3 will not combine with the final test data, right? Will not combine. So the final test is only used at the very, very end.
This final test here is used only at the very, very end. After we've built our model, we have our model, we test it by predicting what it should be on the test set. This is done internally during the process of building our model, because this is done at every single tree that we add. in our process. So at every iterations, we take two of those three subsets for training and one for testing. In the next tree, we take two others of this tree. So at each time it's random, and we use it for training, and then we use the left out one for testing.
Okay.
For testing internally if we're going the right direction in a way, or if we've stalled somewhere because we don't get. And you'll see when I get to the curves, you'll see how that happens in the example.
Thank you.
Other questions?
I think Long, do you want to, you added an image, do you want to,
Oh yeah,
like
train
the
test.
example?
What is it?
I think it's kind
that?
of showing well, an example where you have training set that you have maybe a model. I think the model is maybe the green or yellow line, and then you see it's exact same on the test set, but you see that it's like it's missing.
Okay.
Yeah. I think the line is so it's trying to, on the training set, it's tried to hit every single blue dot or almost as like very close, but then when that exact same line is put on the test set, that you can see there's a number that would be quite a bit.
But again, that's in short, it could be either our 70-30 we originally left out, or it could also be the 2/3 here. This could also be internally the 2/3 and the 1/3
with your K.
that we
Yeah.
test. Yeah.
Yeah.
At every iteration we could test this internally, but it could also be the original splitting.
Yeah, why don't we take the post biologique, the little
yes, it could be now.
Yeah. So we'll say
what time is it?
It's like I see 13 past on my computer, but shall we say 20 past? Come back?
Yes.
Is that okay?
So
yeah.
at
2:20.
Yeah, 2:20.
Yeah. Perfect.
Good.
Thanks, Jerome. Have get a glass of water again.
Yes, mine is empty, of course.
Yeah. Okay. See everyone soon.
All right. Yes. Is everybody back? I guess those that aren't back will not be able to answer. So I don't know if it's a good question to check if everybody's back.
Sometimes people do
Yeah, they just raise their
thumb or turn their video on. I see videos of a number of
Yes, we're back.
people. Looks like most. Okay.
my roommate gave me a decadent sandwich
Ah, very nice.
break, so I don't know how I'm going to eat that while keep explaining.
We'll make sure we ask questions that you can.
Perfect.
You can.
What time? What time is it now
In Santa Barbara? He's down with Costas. And he's not. I guess you're not with Costas, but you're in Santa Barbara.
Yeah. It's 3 hours behind, so it's 11:20.
11:20. Okay.
And it's a beautiful day, about 20 Celsius outside. I wouldn't say it's a bright blue sky. There's a few very high clouds, but it's still a very nice day.
That's where I met Bobine in Santa Barbara.
Santa Barbara.
Really?
Yeah, the IATBR.
Yeah.
Yeah.
It's a good place. Yeah, and you can also see the seaside.
Yes. I don't see it from my house, but it's not far away. It's 2.5 kilometers. The closest beach to our house is 2.5 kilometers. So it's nice. You have the mountains and the sea. It's just an incredible city. It's a little paradise, but it's very expensive and very wealthy. And,
Expensive?
yeah. Oh yeah, the cost of living here is just tremendously high compared to
California.
California in general, any coastal cities in general. Santa Barbara particularly is very, very expensive. Our rent is 3 times what we pay for an apartment in Montreal. Even food is like about 40% more expensive in Santa Barbara than in Montreal. Restaurants, same things. Everything is just so expensive.
Yeah.
All right. Let's keep going, because we've got many. I don't want everything that I've prepared to go to waste because we don't have time to do it. So it wouldn't go to waste, but still. All right. Okay, so we have now a good idea of how we build our gradient boosting models. But the problem with gradient boosting is, how do you interpret those models? One single tree is relatively easy to interpret because you can visualize it very easily. You can see how every splitting variable impacts the probability of the outcome. But what happens if you have 1,000 trees that are not the same? They're not 1,000 exactly same trees. There are 1,000 different trees with different splitting variables at different values of each variables. So how do we do that? Well, the people that are smart enough to have invented gradient boosting also came up with 2 important tools of analyzing gradient boosting results. And these 2 tools are I do think they are 2 of the main reasons why I think gradient boosting is useful, could be very useful for many applications in transportation research. The first tool is to evaluate the relative influence of the predictors that we input in our models. So as I said before, in gradient boosting, you cannot test statistically the significance of your variable. But what you can do is that you can rank those variables based on their importance in the model. And how is their importance calculated? I'll get to that on the next slide. But in the end result of this is that, let's say you have 5 variables, and each variable explains a certain amount as a certain explanatory power. So explain a certain amount of the variance in your that is able to be explained by your model. The second important tool for analysis is what we call partial dependence plot. Partial dependence plot pretty much plot the outcome variable as a function of one of your predictors, having every other variable while what we call marginalizing the effect of every other variable, and it's done by keeping those constant at their means. I'll explain this a bit later on the next slide. So relative influence of predictors. How do we calculate the relative influence of each predictor in our model? It's based on two things. The first is the number of times a variable is selected for splitting in our trees. And the second thing is, what is the improvement in our model when we add this variable as a splitting variable in one tree? Well, it's measured as the empirical square improvement of the model as a result of this. And usually the relative influence is standardized so that it adds up to 100% for all the variables. So if we have 5 variables, in the end, if you add up the relative influence of your 5 variable, is going to add up to 100%. If you have the same model and you decide to add 10 more variables, it's still going to add up to 100%. It means that some variables are going to lose some influence and others are going to gain influence if you add variables to your model. Mathematically, that's how it goes. So you first calculate the influence of variable j, on a single tree t. Pronunciation, French, English, keeps confusing me. So the influence of your variable j on a single tree t is calculated this way, and then where L here is the number of splits in the tree, and SI is the splitting variable being the same as the investigated variable. So let's say we have a tree with 3 splits, and your variable is used once in your tree, then this variable is used in your tree. It means that the value here 1 is gonna mean 1 for this variable. And what is the influence? That's where is the difference between adding this variable with this this variable with this tree to your model and not having it, in a way. And then so you calculate the overall influence of your variable j on the ensemble M of all the trees by averaging its influence over all trees in your model. I don't know how clear that is. One important thing about the relative influence of predictors, influence do not provide us with any information regarding the direction of influence of our predictors and our outcome variable. It means that we don't know if it has a positive or negative influence. We don't know which way it goes. All we know is that it affects the variable in some way, and this way can be high compared to other variables or not. And in short, this is a very useful thing because it allows us to kind of, if we don't know where to start, before doing some logistic regression, let's say, you could use gradient boosting to test out a few variables. Like we have 20 possible candidate variables. You test them all. You realize that 10 out of those 20s are not really relevant for your problem. So you drop these and then you keep going. Okay, we only take those 10. Okay, out of those 10s, 8 really are important. Let's test our logistic model with only those 8 variables. It could be a way to use this.
Excuse-moi.
Yes.
So for Alvin's previous question, he asked, is it possible for one variable be used for more than one time? So for equation 1, that means so if the variable is selected as a split variable, and it will be selected for 2 times, for example. Sorry, you are muted, Jérôme.
Because I was taking a bite of my sandwich while you were asking a question. In practice, I don't think that the algorithm we use, it's possible, but I do think that it could theoretically be possible, but I don't think it's happening in the way the algorithm are coded right now. but I'm not 100% certain about this. It's a good question. I should have a way to note those questions and to kind of look it up. I don't know where I could. Where was my thing? Anyways, should have prepared this.
So
Yeah.
for equation 1, it only means how many variables was selected in the tree G, right? In the tree T.
In the tree E.
T.
I. I is the number. I is the tree, and J is the variable. So the way it works is that, as I said, we can have 10 explanatory variables in our models, but our trees only allow for, let's say our trees has 4 splits, so it means 4 variables can be included in each tree. If a variable is often included in a tree, it means that this variable seems to be important in the model. So it considers its influence only when the variable is selected for a tree. If a variable is not very important, it means this variable will not often be selected by the model in the tree building.
Yeah, so I is the number of the split, right? L and I.
Yes.
I is a split. So you just to confirm if this variable is selected or not for each split, right?
Yes,
So
pretty much.
you then sum them up. So the meaning for equation 1 is that how many variables were selected for the tree. I don't know if my understanding is correct.
No, because there's something called the I. Yes, it's a bit confusing. I should have used a different one. This I here. Let me note this thing here. I'm not even this one here. It's the empirical. I should have used capital I. Is the empirical square improvement as a result of this split when the variable that we're, let's say our variable here is population density. Density, you understand, perfect. Let's say our variable is population density. If population density is the splitting variable in our tree, then we can calculate its square, the square improvement that including this variable in our tree leads to. And we sum this at every split in our tree.
Okay, you mean that each variable have improvement for each split?
Well,
Note.
yeah, but this improvement it could be very, very small. So that's the point.
Okay.
The variable could be there, but the improvement that the variable brings is very small, and thus the influence of this variable is not going to be very high.
Zero. Yeah. Oh,
because
okay.
yes, it comes often it comes back often in our trees. It's selected often as a splitting variable, but every time it splits, it does not add so much to the model. So because of that, the influence of this variable is not going to be very high. But in general, it tends to be that if a variable is used often, it's because it is useful for the model to use this variable often, and so its influence might be higher in general.
So is it possible that for split 1, so this variable have very high improvement or influence? For split 2, the same variable also have very high influence. So is it possible?
Yeah, that's asking a question if the same variable can be used in more than one split in the same split.
Yeah.
Which is, as I said, I don't think it is.
Oh, okay.
One variable is only used once per tree, but by including this variable in a tree, in short, you consider this only when but then again, why would there be a sum there? You're right. Let me just pop something, which is a reference I took for this. Where is it? Here. Let's cut this here. Okay, maybe I did not. The influence of the variable J in a single tree T. Consider that the tree has L splits. Therefore, we are looking for all the non-terminal nodes from the root to the This gives us the definition of variable influence. This measure is based on the number of times a variable is selected for splitting, current splitting. Okay, so you're right. No, you're right. I was wrong. Okay, you can use the same variable for splitting several times in the same tree. And so every time that variable is used to split a tree, you calculate you estimate the empirical square empirical improvement that this split as a result of this variable brings. So in a single tree, it means that one variable could be used several times to split the same tree. And then, so that's why you add up. That's why we add the square improvement here. That's where there's a sum, because at every split of our tree, this is for one tree. This thing here is for one tree, and this is the average over all trees. For one tree. So if a variable is used twice in the same tree for splitting, and the empirical improvement, let's say, is, I'm giving a random number here, 0.5 the first time and 0.6 the first time, then we sum this, and it gives us 1.1 as empirical square improvement due to this variable in this tree. And then we average this over all trees in our ensemble. Maybe that makes more sense this way.
Okay. Then we get the influence for every variable.
Yes.
Okay.
That's how we get the influence for every variable. Okay, I was taking a bite, so that's why I muted myself. I didn't want the recording to record me eating my sandwich, which is getting cold anyways. Okay, so if this is clear for the relative influence of predictors, again, you will be able to look this up in those two references here. It's very well explained in Maitken and Knoll, which is the paper I just shown, and in the book by Hasty, Tibishakarani and Friedman, chapter 10 explains very well with slightly different notation, the same way that the relative influence of predictors is calculated. Which brings us to partial dependence plots. This is the second interpretation tool of gradient boosting. So what does it do? Partial dependence plot shows us the average change in the outcome variable if we're modeling a continuous variable, or in the log odds or the probability in the case of a binary response variable, as we change the inspected explanatory variable j, holding every other variable constant at their means. So it's kind of trying to assess what does a variable do, what's the relationship between this variable at its different values and the outcome variable, or the probability in a case of classification. It kind of provides a very useful basis for interpretation, because this here gives us a direction of influence. If our outcome variable or our probability goes down as we increase the value of our predictors, it means that this has a negative effect on our outcome variable. So it kind of gives us the direction of the influence by looking at how it's made. It's very interesting because it allows us to also investigate nonlinear relationship. It means that the relationships between our predictor and our outcome variable is not necessarily linear, and we're going to be able to investigate it using these partial dependence plots. You'll see a further example later where you'll see a fast drop after a certain values and then no change after another values. It could be that it could also, let me see here, this could be done like whoop and this. So you would see that like past 6 here, you wouldn't have any more change to your outcome probabilities. So this is kind of the strength of those partial dependence plots. It allows us to investigate if there are threshold effect and nonlinear relationship between our predictors and our variable. And we can draw these partial dependence plots, one plot per predictor in our model. What else is there on that slide? Okay, yeah, this is good, but it's also, we got to be careful with the interpretation when there is very strong interactions between our explanatory variables. It kind of control for the other variables, but it's a kind of crude way of controlling this by just taking the other values of the variable at their means. The correct way to do, the optimal way of doing this would be to numerically integrate out all other variables over a suitable grid of values. But in practice, this is so computationally intensive that it's never done this way. So the easier approach is just to fix the other variables at their mean values. I do think there are ways that you could specify that there could be fixed at other values than their means. If the variable is if the other predictors are categorical variables, it's fixed at the largest category. So that's how we are able to build these partial dependence plots. Again, you can learn more about these in the paper and the book. They're going to give you a bit more mathematical background on how exactly this is done. But I haven't seen as many equations explaining this than I've seen for the relative influence, for example. And you can also produce pairwise partial dependence plots. So using 3D or a false color, you can see what is the influence on our outcome variables of variable A and variable B together. So when you reach a certain level for your variable A and a certain level for your variable B, it gives us a certain values. You'll see an example later where I use false color to express that, to express the relationship between income and density, for example, on car ownership. This is the example I'll be showing later.
Looks like Bobin has a question.
Yeah, sorry. So
You give him a chance to, it gives him a chance to eat.
Please. Yeah, because for the carvid, you said that the reference will be limited if there's some interaction or correlation between the explanatory variables, right? So does that mean the explanatory variable should be independent with each other for the model?
In the perfect world, yes, but you know that it's never the case. They're always somehow correlated. And not only are they correlated, but there could be special interactions between those variables. And we know that's the case. We know that it's the case, for example, if you include like income, for example, as a different, will have a different effect on modal choice, depending on the characteristics of the built environment. When built environment is very car dependent, very low income people will still be traveling by other means than the cars, while everybody else will be traveling by car. So there is some sort of interaction this way. So that's an example of interaction. This is just a two-way interaction, but it could be more ways interaction between variables. And so it's just that it gets harder for this method to really give you a precise partial dependence curve when there's complex interactions between the variables. In truth, I have not seen many explanations onto why this is exactly. It's just that every time I read about this, it says that you got to be careful when interpreting those if there are strong interactions between your explanatory variables. And as I said, I would guess it's because the way we do it is that by fixing every other variable at their means, but it's kind of a crude and imperfect way of marginalizing the effect of the other variables on your outcome variable.
So when you conduct the research, do you need to do some correlation analysis first for the independent variables? Okay.
Exactly.
Oh,
yeah.
so
this should always be done anyway in any model.
Okay. Even for machine learning method, right? Because when we do some regression modeling, we need to confirm that the independent variables are independent with each other. And so I don't know if it's also the same for machine learning method.
Yeah, it's a good question. One of the things that is put forward as like why GBM is good is that apparently it is immune to a multicollinearity between explanatory variables. It is in a purely predictive manner. It means that, coming back here, for this, it does not matter. Let's say you have many variables that are correlated to each other. The process is going to select the variables that are the most relevant for your model and leave out the variables that are very correlated to this, to the best variable, but not as good. And so for predictive, if your only goal is to predict your outcome variable, the multicollinearity issues between your variable is not important in gradient boosting. That's what's been repeated in many texts that I've read. But when you dig deeper, you understand that it is true only for prediction. If your goal is to predict the outcome, it doesn't matter. You can put in there as many correlated variables as you want. It does not matter. It's not going to affect the. It is not going to affect the predictive power of your model. However, when it comes to interpreting the influence of the variables through the partial dependence plot, what we've noticed is that it can change things. It can change things because, as I said, this could affect the curve that we're going to be shown. It also, it's not true that it does not affect this. It does not affect in predictive power, but it's going to affect the relative influence of predictors. Let's say that you have two predictors that are very correlated to each other. The algorithm is going to choose one of them because this variable is slightly better at explaining the outcome than the other. So it's going to choose this one much more often. So in your result, this variable is going to have very high relative influence, while the one that is very correlated to this one is going to have a very low relative influence because all the relative influence of the combined effect of those two variables are going to be taken up by one of the variables. I don't know if that's cleared.
Yeah, I understand. Yeah, because for example, we have speed, the time, and also the travel distance, right? So maybe these three are correlated. So if you put them together, so the prediction is very high. So that means these three variables give a great contribution to the final decision. So, but however, when you decide which one have more influence, so maybe they only select two of them, maybe 30%, 33% for each one. But actually, these three variables are correlated with each other. So actually, you should select all of them. They are both important for the prediction.
Yes, exactly.
Yeah, exactly. But if you only decide, okay, if you only want to choose two of them, so maybe you only select the speed and the travel distance, and dispose the travel time or something. So is that correct? So
that is very correct.
Yeah. So however, the sum of the contribution should be the same, right?
Yes.
So if you put the three variables inside your model, the sum is maybe 70%. But however, if you only put two variables inside, the sum should also be 70%.
Not exactly, because that third variable might be highly correlated with the first two, but there's still slightly something more that this variable is explaining. So not having this third variable might say that like you're explaining 65% with only two, while you're explaining 70% with three variable. But in truth is this method does not allow you this. It does not tell you exactly the split between those three. It's going to tell you a number, but that number might not be theoretically relevant. One example that we have in our paper that in the last paper that I've submitted, the number of Bixi stations, bike sharing stations in Montreal, seem to affect the decisions of car ownership. It's correlated with the decisions of car ownership, but it turns out that this variable is also very highly correlated with communauto, car sharing locations. And so it's kind of sharing some variance with car sharing, with a car sharing variable. And when you think about it in a theoretical manner, is Bixi really contributing that much to explaining car ownership? Or is it more that it adds globally to the options of mobility resources available, but on itself, it might not be so relevant. It's just that it's correlated with other variables. So it's taking up some of the explanatory power of other variables and taking it for its own, if that makes sense.
Okay, so finally you only choose, you dispose this variable or include both of them in your
We
paper?
kept both of them, but
Ah.
we noted in the text that what I just said in a way. That's why we have to be careful in the interpretation of the results with the relative influence of variables and the partial dependence plot because of correlations between variables.
Oh, okay. Thank you so much.
So if you read about GBM and it tells you that it's immune to multicollinearity, it is only partially true. It's true only if your goal is to predict your outcome, but it's not true if your goal is to analyze the influence of your variables and the relationship between your variables and your outcome variable.
Okay, perfect. Thank you.
Okay, moving on. We're almost at the end of the theoretical part. I didn't know it was going to take that long. Yeah, we see. So I was supposed to find time to add some funny gift about things being incomprehensible up to this point, but hopefully it's not. So do you guys have any other questions before we move on to, I have prepared some R marks down files for you to show how we can do this in R. For those of you who are familiar with R, if you're not familiar with R at all, you can still follow the example and try to reproduce the same in Python later. Or you can even leave the tutorial, this workshop, if you don't feel it's good for you, but I'm going to move on to the rest. So is there any more questions? Bobin, you still have your hand raised.
Oh, sorry. Maybe I just asked a little question. So for the overfitting, I mean, to defeat the overfitting method, you have subsampling and the cross validation, right? So do you think the cross validation is better than subsampling?
We kind of use both of them. You'll see in my example that I use both.
Oh,
I use
okay.
cross validation and splitting the initial data set into a training and testing set.
Okay, that's interesting.
So by using both, it's kind of a double validations that I'm doing.
Okay.
Great. You don't have to do this, but from what I've read, it's better to do this because it gives you even more robustness in your model if you double validate it this way. Validate it internally with the cross validation, and then validate it externally with the subset, the testing subset that you left out at the beginning.
Oh, okay.
All right. I'm gonna okay. I have to stop the sharing because I'm gonna share my other screen now. Just give me a second. Okay. Sharing again. Screen number 2, share. Okay. So you see gradient boosting machine workshop. Looks like a text file, but it's not. Perfect. Okay, I can have this here, I guess. Okay, so we've seen the theory behind gradient boosting. It was very good. Now I have a much better idea of what else I should include in this presentation to make it clearer, of the part that were not as clear. Example with diagrams of trees and stuff like that. So now we're going to see how we can implement this in R. But the whole process kind of apply. As I said, you could take the whole general process of how I'm doing it and do it and code it yourself in Python, for example, if you're more fluent in Python. I really don't know how much you guys know of R coding. Maybe some of you are even better than I am. So maybe you'll see things that I do that are not optimized. And as I said before, there's so many ways of doing things in R that you might have your own way of doing certain functions. But the idea today is just to like kind of explain to you really how you want to build a model from scratch if you want to run it and test it on your computer. You're going to have access to this. I've prepared 3. These are called R Markdowns files, which allows you to display it in HTML, but you also have access to the code. I'm going to include, when I'm going to send all of this to you, probably tomorrow, in all truth, you're going to have access also to the data that I've used to build those examples. And so let's get going. So there's 3 ways to do gradient boosting in R. Well, 3 main ways. There's the GBM package, the XGBoost package, and the H2O package. The H2O package, I'm not going to talk about it because I know it's out there, but I've never tested it. I've never tried it. I haven't read about it, so I don't know how to use it. If you know, great. If you want to use it, you might want to read about it, but I'm not going to focus on this one today. We're going to do one example with gradient with the package called GBM, and one other example with 2 other examples with the XGBoost package. So of course, first we install those packages. If they're not installed on your computer, you have to install them first and then load them in your in your R session. Okay, the first question is, why should you use the GBM package instead of XGBoost package, for example? Each package is slightly different. GBM is the original implementation in R of the GBM algorithm by Jérôme Friedman. It implements stochastic gradient boosting. It supports classification and regression trees. It can incorporate many loss functions depending on the type of outcome variables that you have. It has what they call out-of-bag estimator and cross-validation methods to find the optimal number of iterations and avoid overfitting. And it requires less data processing. That's a pro versus XGBoost. It requires less data processing than XGBoost, and it supports categorical predictor. So if you have a predictor that has 3, 4, 5 categories or more, it can be used as is in GBM, while it's not the case with XGBoost. I'll explain that later. You got to be careful though to not overfit, as I said, because there's no automatic stopping function in this package. So the first step, of course, is to load the data. For this first example, what I'm using is the Canadian census data, to which I added some built environment characteristics. I could have not done it, I realized, but anyways, that's the data set that I had. You're going to have access to it as well. The idea here is that we're going to try to predict something, and that something is the percentage of, so here I'm displaying the code names, I'm displaying all the variables that I've included in the data set. We're going to try to predict the percentage of people that are commuting by active travel in each dissemination area. So our data set is a list of, each observation is one dissemination area. For those of you who are not familiar with that, dissemination area is the smallest unit in the census, in the Canadian census, for which all variables are available. In truth, there's a smaller unit called the census, the dissemination block, but at the dissemination block level, which is really the street block, all we have is population. So if you want all the variables, you have to go to dissemination area. Dissemination area is slightly smaller than census tract, but unlike census tract, it covers the entire Canada, not just metropolitan areas. And so this percentage of commute active travel is a discrete, not a discrete, is a continuous variable, which range from, as it's a percentage, so it ranges from 0 to now 1%, of course, but 0 to 0.60. So we're going to try to model that with gradient boosting. I've included stuff here because you might learn things in R if you're using R, but you're not super expert in R yet. For example, to inspect your variable, which is always a good thing to do before you start any modeling, I use the library called Summary Tools. What Summary Tools does is that in one function, you can pretty much extract all the descriptive statistics of the variables that you want. So it gives us an idea of the distribution of each of our variable. How many missing values might we have for variables, which is kind of very useful. So always a good thing to look at your data this way before starting any modeling. I've also displayed it in a single very long table here. As you can see, the table, so first, let me go back here. Some of the variables that I have are like census extracted variables. So all these, for example, percentage of population, age a certain age, population density, percentage of detached house, percentage of household owner, the income, the median income in the dissemination area, education, employment. These are all, and the commuting, these are all census variable that you can get yourself from the CHAS repository. If you didn't know about this, it's where you can download any data from the census at any geography level of the census, pretty much. And the other variables are the built environment variables that I've included. There are two types, the ones that I've computed inside each dissemination area. So let's say we see EPIC here. What is EPIC? It's épicerie. Épicerie is grocery store in French. INDA means in the DA. Well, I've also computed those within a certain walking distance buffer around each dissemination area centroid. But anyways, we're not going to use all those variables. It's just to show you what it's in there. You'll be able to play with that if you want. I'm sharing all those variables that I've calculated with all of you, so you can have fun and maybe find some nice research question to answer and nice paper to publish. All right, so we're going to try to model our percentage of commuters that use active travel. Active travel is the sum of walking and cycling. So that's what our outcome variable look like. Sorry. So we can see that it's not perfectly, the red curve here is what should distribution look like if it was a normal distribution. So we can see it's not a normal distribution. But it's not such a big deal for a non-parametric method such as gradient boosting. So you don't really have to transform it. You could. I don't know if it changes anything, to be honest. I've read that if it's a monotone transformation, it doesn't change anything. So we can keep it the way it is. It's also easier for interpretation if you keep the variable as it is, unless you have to transform it back. So what are dissemination area? I didn't have time to go and extract the nice map of the percentage of people commuting by active travel. So instead, I've put a map that I already had, which is the map of vehicle per 1,000 adults. So the car ownership rates within those dissemination areas for Montréal, Laval, and Longueuil, which are the three regions we're going to use for our analysis. Okay, as I said, Bobin, that's where we're going to do the first split. Okay, so first, before we do the splitting, as I said, gradient boosting can handle missing values in the predictors. If you have missing values in the outcome variable, you're going to have an error. It's going to tell you that it cannot run the model because there are missing observations for the outcome variable. So you have to extract those to take them out, to only take the observations for which you have the value of the outcome variable. If you don't have it, you have to exclude those observations, but you can keep observations which have missings in any other explanatory variables. So we split the data set in two. I'm going kind of fast over the code, but you'll be able to read it yourself and understand what I've done. And one thing that I haven't said, if you have any question whatsoever about any of the codes that I've done, you can ask it right now, or you can ask it anytime later in the future when you use this code as example. I'll be more than happy to answer. I'm available on Teams, so I'll be more than happy to answer that. Okay, so we split, as I said, we split our data set. Our data set has about 4,000, how many do we have? Okay, 4,514 cases. We split that into 70-30. A 30 that we reserve only for testing, we're going to use it at the end, and we're going to train our model only in the first 70%, not the first, but a random sample of 70% of our data set. This is what I do here in this block, in this code chunk. Next thing, for GBM, you have to define the formula of the model the same way you define it in most model in R. So if you do a linear model in R, you use this way of formulating your model. And this way is this. You put your outcome variable, the one you're trying to predict, on one side of this little thing that I don't know how it's called. How is it called, Owen? You know?
Tilde, I think.
What? I missed
Yeah, Meredith. Yeah. It's like tilde. I don't know if it's a tilde or tilde. Meredith has written tilde.
I heard
Tilde.
tilde like yeah, but I don't
Yeah.
know if it's the French pronunciation or the English pronunciation.
Yeah,
Tilde.
I think I
Okay.
feel like I feel like it's tilde possibly in it. But
Tilde?
yeah. Or-
Anyways,
yeah. Say tilde. A tilde, sure.
so I would say that's another advantage of GBM versus XGBoost. GBM is simpler to use because of this, the way you define your model. So this is a very common way in R to do it. You select your outcome, you select your predictors, and you list them like this. So the predictors are just added with a plus. Super simple. So you can define the formula first and then insert that object formula here in our model. This is what I do. And then once we've defined our formula, I've selected a random bunch of variables based on what I know. It's not random, but we'll see what it tells us. So once we're selected what variable we want to use for first iteration of the model, for first model, we go on and we train that model. As everything in R, I highly recommend that you look up what does the GBM function does. So you perform GBM in the GBM package using the GBM function. That might be confusing, but or maybe not, I don't know. And as in R Studio, you can always look up for what the function does in the help panel here at the very bottom right, normally, of your R Studio interface. And it tells you what are all the parameters of the functions and how these they also give you the default values for those parameters. So it's important to know that if you do not include a parameter, R is going to use the default values supplied by the package. Okay, which comes to our hyperparameters. So as we've seen earlier, there are a different number of parameters, hyperparameters that needs to be 2. The number of trees, the learning rate, which is the shrinkage, how fast should we go down the gradient, the tree depth, so how many splits in our tree, which kind of controls the interaction, the possible interactions between our variables, the minimum number of observations in each node. So at each extremity of your tree, how many observations should you have? Well, not extremity, but at each splitting of your trees, how many observations should you have there? Minimum. A fraction of rows to subsample. This is the bag fraction, and this very parameter is the parameter that allows you to do stochastic gradient boosting. If you set this parameter to 1, I should have included this. If you set this parameter to 1, it means that your gradient boosting is not going to be stochastic. You're not going to have this random aspect to it. So it might not be as good. And the percentage fraction to subsample, this is not available in the GBM package. And so I personally, time how much time it takes me to run my models, especially when I know that the models takes several minutes. So I've included a way for you to time model in R, because R does not have an automatic way of counting. Well, you have to calculate how long it takes to run model. So here I've put it in comments because it's for technical reasons. Because when I published this HTML, I didn't want it to rerun the entire model, and it takes 5 minutes of my time to do that. So I've just commented this and loaded the results later for interpretation. So what I've included here, you can see the type of distribution you want. So since we included a continuous variable, we can use one of the 2 or 3 continuous distribution available on the GBM package, which is Gaussian, Laplace, or T distribution. The data is the data that we've prepared. So our trained data, which is 70% of our original samples. We first start with the number of trees that is set to 5,000. Why 5,000? We want a number that is high enough that we are pretty certain that we're not gonna reach that number, because in the end, we want to find a smaller number of trees that's going to be able to optimize our model. So it's kind of the upper limit. The interaction depth, I've put at 3 for now. 1 would be a stump, a tree with only 1 split. As I said, 3, I've decided 3, it could be more. We'll see later how to decide that. And then the other variables here, it's pretty standard. Cross-validation fold, I've put 5. It means that in the procedure of building the model, we use 4/5 of our training set for training each iteration, each tree, and 1/5 is used for testing. This is where the cross-validation comes in, Bobit. Then personally, I always save my model afterwards so you can load it later, especially if it took some minutes to run. You wanted to have it on hand later without having to rerun it again. So I save it, and then you can load it again, and then we can analyze the results. The first thing you want to do, so you've run your training set, you've run your train model on your training set. The first thing you want to do is, how good is that model? Vincent Aubry-Legros raised the hand. Yes, go ahead. If you're speaking right now, you're muted, so I don't know.
The function from the to save the model, is it from your
The
package
package?
or it's from another package?
Good question. Something I haven't explained. Do you use R, Vincent?
Yes, I use R.
Okay.
And then
Okay,
I
so this
found
is very
this,
something
function
very convenient to use.
Yeah.
A file that is .rds is the default saving format in R. You can save any object in R as .rds, and it's kind of the fastest way to save and read an R object that you want to save for later. So it's not part of the GBM package. Save RDS and read RDS are base R functions. I strongly recommend to use that. You can save a data frame with that. You can save a vector. You can save a list. You can save anything with that. So what I do is that I save your model. It tells you here, you want to run this model and put it in this object GBM fit. And then I save GBM fit with save RDS. For XGBoost, there's something different. I'm going to come to it later. But yes, so if you didn't know about this, there you go.
Yeah,
now
I
you can
will
use
this for sure.
Very convenient. When I stumbled upon this, like, I don't know, a year ago, I was like, oh my God, this is life-saving.
Yeah.
So super useful.
Thank you.
Okay, so this allows me here, as I said, so instead you've run your model, especially with models run very long to run. You run it once, perfect. You want to save that, and then so whenever later you don't want to keep your R open, you can just load it again using this. You make sure you save it for posterity. So we read it, and then we're going to inspect this. We use this function here, GBM perf, to find the best iteration. This function produces two things. It gives us which one is the best iteration, and it also produces this plot here that you see here. What is this best iteration? We can see there's two curves on the plot. The black curve is the curve of our 4/5 of our training set. Is the training, the part of the training set that was used in the cross-validation process. And the green one is the cross-validation subsample that we left out, the 1/5 of our training set that we left out. What we see is that after 2,957 iterations, there's no more improvement in the square loss value of the left out subsample of our training set. What this means is that it does not matter if you run 5,000 iterations or 3,000, we're going to get the same results. And this is where the question of overfitting comes in. If we were only testing and seeing that we only use the black curve, which is the training part of the training set, it keeps going down, and it would keep go down all the way to 0, asymptotically to 0, if we didn't stop it. but we don't want this because this would be overfitting. So this tells us where to stop to make sure we do not overfit our model. And so here we have the number of iterations we should use. No point of using more in these parameter conditions. But as I said, shrinkage, which is the learning rate, is also linked to number of iterations. If you reduce this to a smaller value, you're going to need more iterations to reach the same level. You can also get the root mean square error, which is, it doesn't tell us anything on its own, but it gives us something to compare to a bit later. Okay, so this is only internal, using internal validation, a cross-validation process. Now we're going to try and see, okay, what about the 30% of our sample that we left out? So the next thing to do is we want to use the model that we've trained, whether 70%, and use it to predict our outcome variable, which is the percentage of commuters by active travel in each dissemination area for 30% left out test sample. So we use the function predict. Predict is a general function in R. You input the fit of your model output, and you tell him the other information it needs, and you can predict. What the prediction gives you, this will give you a vector of the value, the predicted value of your outcome variable. And then you can compare this predicted value with the real value. And in the case of a continuous variable, calculate and root mean square error, which is going to be this. So how good is this? Well, we can see that through cross-validation, so the train at 3,000 iteration, the train set, the 4/5 of the train set gives us an root mean square error of 0.0427. The cross-validation, so test, which means the 1/5 of our training test gives us this value of root mean square error, and the final 30% that we did not use at all for training our model gives us something very similar to our cross-validation value. So it means that the cross-validation kind of works. It tells us where to stop to not overfit, which is good. Okay, so now we've assessed that our model is good. Now we have two ways here. First, you can go and inspect the different outcomes using the different interpretation tools, or you can straight away try to fine-tune your model. We're going to fine-tune our model after looking at first what does our model tells us. So there are several ways to produce the relative influence of predictors. I'm showing you a few ways here. There are built-in functions to do it, but these built-in function gives us very shitty, what I think are terrible charts. But you can always customize this later. The idea is that in our model, the main variable, the variable that has the highest relative influence in explaining the percentage of commuter that use bicycle or walking, is the distance to the distance between each dissemination area centroid and the downtown of Montreal. And the downtown of Montreal, for those who are interested, is taken as the streets of Peel and Sainte-Catherine. So this is by far at 45%, you can see it here, 45% is by far the most relevant variable in our model. These are the other variables. You can see it explain much less, and we can go all the way down to like, is there a train station in the dissemination area? It does not explain whatever, 0. Some of them explain less than 1%. So it tells you like what should be included or not, but it also can tell you that like these way of calculating those variables might not be the best way. For example, the number, if there's a metro station within the dissemination area, it does not tell us much, because you can be on the verge of a metro, like one street away from a metro station, but that metro station is located in another dissemination area. So it tells us that these variables are either not good at all or just not calculated the right way. In the case of built environment variable, that's what I've came up to conclude after several testing. So anyways, it gives us this list, this ordered list of variable ordered by relative influence. So you have the plot, but you also have the values themselves in a data frame. You can also use other packages. There's a package called VIP that is good for interpreting results of machine learning methods. The function is very simple. You can produce the same graph with all the variables that you want to include. Anyways, you can look this up when you're going to look more deeply at this code. Which brings us to the second interpretation tool, is the partial dependence plot. Again, there are built-in functions to do it quickly, and there are more complicated functions to do it and customize your plot in a nice way. So because our distance to the Montreal CBD is the most relevant predictors, I've decided to plot this one to see what's the relationship between our variable, which is the percentage here. Y is a percentage of people commuting by active travel. And our predictor that we're inspecting is the distance to downtown. So you can see a partial dependence curve on this plot. What we see here is that after 10 kilometers away from the center, there's no more changes in the percentage of people commuting by active travel that is attributable, that can be attributed to this variable. Does that make sense? But when I know you've seen those plots so many times in our weekly
meetings,
meetings.
It's clear for me, but
yes, very clear.
Did
good,
you? Because I remember when we initially did this partial dependence plot, that the y was not like the percentage. Is that right? Yeah.
It's a very good question.
So have you done something in your coding that shows the percentage? Okay. Yeah.
The y in those plot depends on the type of variables that you're modeling. In this case, in this example, since we're modeling a continuous variable, the outcome of the y-axis here is going to be the values of our outcome
it's the
variable.
percentage of the people in that dissemination area who,
in our case, our outcome variable is the percentage of commuters in the dissemination area commuting by active travel. So it's also a percentage. It's a bit confusing, but let's say we were trying to predict the median income in the dissemination area, then this y here would be the median income in relationship to distance to the downtown, for example. But this plot is slightly different in the case of if your outcome variable is a binomial values, is going to give us something different, which is the probability to have the one value in your binomial outcome. This is where, and there's also a trick, but I'll explain it later, Owen, because your question is good. So we'll come back to this, but in a continuous variable, your y is your outcome variable, is the dependent variable you're modeling. So the values here are the values of your dependent variable. So you can simply produce this with a simple.
Can I ask you a question?
Yes.
I'm not sure if you had mentioned it before or not, but I want to know if we need to create this partial dependence plot for each independent variable.
Yes.
Okay.
So in short, what we tell R to do here, in this very simple, quick way to do this, we tell him to use the output of our model, so our GBM fit, which is the output. We save our model as the object GBM fit. We're telling R, take this object. In this object, you're going to see this variable here. We want you to produce the partial dependence plot for this variable here. So we select which independent variable we want to show the partial dependence plot for. This could be any of the variables that we've included in our model. I selected this one as an example because this was the variable with the highest relative influence in our model. So we wanted to see how was the variable related to our outcome variable, which is percentage of commuters by active travel.
Thank you.
Does that answer your question? Yes?
Yes, exactly.
Yes. Good.
So sorry, I also have a question. So for the partial dependence plot, is it only used for continuous dependent variable or continuous outcomes variable?
No, you can produce the same plot for if your outcome that you're predicting is a binomial outcome, for example, a yes or no question. What this plot will tell you is the probability to have yes, instead of the y being the value of your outcome. It's going to be the probability of having that yes in your yes or no question.
Okay. How about if I have 5 categories?
So in 5 categories, it's going to be the probability. Do I have an example here? Let me show you here. Okay, here. These are examples from my most recent papers. The influence of average age on the probability of belonging to 3 car ownership class, distinct class, no vehicle, less than 1 vehicle per adult. So I'm skipping ahead here, and 1 plus vehicle per adult. 3 distinct class. So here it's a model with 3 classes. The curve tells you the probability to belong to that class relative to the probability to belong to the other class. So you can see 3 curves in the same graph. It means that as our age variable changes, it changes the probability to belong to one of the 3 classes. And because the probability always sums to 1, that's why those curves seem to be related. Does that make sense?
Yes. Yes. So the higher the probability means the higher correlation between this variable with the decisions, right?
Well, no, it's more like the outcome, and then the line itself. It's almost like I don't know, how much it changes. I don't know.
Yeah,
It's like the influence.
Yes. So what's important here is the difference, the changes in probability as you move along that predictor. That predictor here is our average age in our household. Okay. As you change that, you change the probability. Now the exact values of this, it's based on if you average out all other variables, it gives you a probability of having less than 1 vehicle of like 50%. So you start from there, and then if you move only, so you restrict all other variables to their means, and then you only move this specific variable you're investigating along its values and see what happens to the probability moving only this variable, holding everything else constant. But this initial value here on the left, on the y-axis, it's not because it's higher here that this means that let's say then this one here, like, okay, you see this one here is 53 for the green curve, and this one is 50. It doesn't mean that this variable 53 has a higher importance than this. On the opposite side, you see the relative influence here is higher than here it is for this variable. What it just means is that it starts there and it moves from there. So what's important in those graphs is how it changes, because the initial value is based on all other variables. So you can't take it as granted that it means that this variable is more important than the others. For the variable importance, you have to turn to the variable importance plots, or the value of variable importance is as here.
So the partial dependence. So it only shows the changes of the probability with the changes of the predictors.
Exactly.
But the value have no meaning.
The value are relative. So yeah, they have no meaning because they are the values like that are only attributable to this variable. So that's what it took us a long time, I must admit. Owen can tell you about this. It took us a long time to really realize that it didn't matter. But when I read more about this, I realized that no, it does not matter, because it's based on every other variable in our model. In a way, if your model had only one variable and the variable was the average age, then this absolute value here would be important, but it's not the case. So what matters is the difference between how it changes, how the probability change based on that single variable, holding every other one constant at their mean value.
Mm-hmm. But the Ri is the relative importance, right?
Ri is the relative influence, yeah, or relative importance.
So this one is important. So this value shows the importance of the predictor.
Yeah, this value, the 10, this is something that I've added because I've linked the results here. You can see it here. Adult age 9.57 is the fourth most important variable in this model. And so I've investigated here, and we can see how it changes. We can see that it's not a linear relationship. Here, as age, the average age of the household, average age without the children increases up to about 45 years old, your probability to have one vehicle per adult increases, and the probability to have a shared vehicle in your household decreases. But then as people grow older, when you're up at like the average age of 80, you're more likely to have one vehicle per household, less than one vehicle per adult in the household, and more likely to have, less likely to have one vehicle per adult.
Yeah. So another small question is that, so for the outcomes, it could be category variable or continuous variable. How about the predictors, the independent variable? So it must be category variables, right?
It's a very good question again. So the predictors can be any types of variables, but they're coded differently in XGBoost and GBM. So in this first example here, we're using the package GBM. I don't have any categorical variable in this example, but you can use categorical variable. What it does is it tests every categories, and it uses those categories in the decision trees. So the predictors can be any variable, any types of variable, can be continuous, count, dummy variable, categorical variable, ordered or unordered variables.
I remember when you show the tree. So for each split, so you give us the example that, for example, the income is less than 1,000 or higher
Exactly.
than 1,000. So
yeah.
Income is continuous variable. So does that mean we need to categorize it into different groups for
yes
the tree?
No. Okay, if it's a continuous variable, the algorithm does it itself. It cuts where it thinks it should cut that continuous variable to make it a splitting values.
Okay.
If it's already a categorical, because income sometimes, in the case of census data, income, the median income is a continuous variable. In the case of origin destination data, if you have OD data with income or any other survey, mobility survey data with income, it's usually categorical data. We don't ask people to write down their income. We ask them which income category they are in.
Yes,
So let's say we have, and this is what I use later, if we have 4 income categories, then income can be used as a splitting variable, and it's going to split the tree 1, 2, 3. Let's say this is 0 to 30,000. This is 30 to 60,000. This is 60,000 to plus. And this could even be unknown. If you don't know the income, you can even include it as a category. Maybe it can tell you something.
Okay,
So this is
if it's continuous, the algorithm will give you the cutoff.
Exactly. If it's categorical, it doesn't have the choice but to use a category you provide. If it's continuous, the algorithm might say, no, it's not 30K, it's 45K.
Okay.
It's not 60, it's 70K, for example.
Okay.
The algorithm is going to choose where to cut to make a split in a tree.
And also for the partial dependence Polite method. So the independent variable, if it's category variable, it can also give us the plot.
Very good question. So I realized that I did not include an example. What it would look like. Let me clear that drawing. And do I have some?
For example, the gender, it doesn't have any
the gender.
meaning.
So what you're going to see is, how can I draw this nicely? Do I have one already? Not sure I have. Let me see. I think I do, but just give me a second. I can find one example very quickly so you have an idea of what I'm talking about. GBM, one person, 5. Do I have this? Do I not have this? Where is it? It's going to be points on the, oh, I think I have it here. Wait, no, I forgot. Okay, I did not include it. I can find out one. Okay, let me draw it to you then, what it's going to look like. It's going to change. It's going to be points. It's going to be a point chart. You're going to have your plot is going to look like this. You're going to have your the different category of your outcome, cat 1 of your predictor, cat 2, and so on. Here is going to be your y, your outcome variable. If it's a continuous variable, it's simply the value of the continuous variable. And then you're going to have points. Let's say here is that cat 2, the probability or the value is here. In general, the value is here. The value is here for this one. They're not linked. They're just points. The average value, when the average value of your outcome variable, when this category is used, when a tree uses this as a splitting, this is what's going to give you. This is going to be the average value of your y, considering this variable for this category.
Okay.
Considering holding every other variable constant at their means again. So it's a bit less insightful. It gives us a bit less information than a plot like this, but it still can give you information about the direction of influence. Because you could see, for example, that if this is low income, less than 30K, then the probability of like being motorized, or the number of, or the whatever value you have for your outcome variable is going to be lower than if you're richer, for example. Does that make sense?
Yeah.
But it's good. It reminds me, I will include an example of partial dependence plot with discrete variables, so you have a better idea of what it looks like.
Yes, thank you so much.
It can also, because it can also informs us on, it's going to be a bit like the results in a, you know how if you include such value in a categorical variable in a logistic regression, you're going to have a coefficient for each of your category of your except for the main category, where here you're going to have a value for all categories. Okay.
Sorry, I have a question. Like in a statistical models, let's say, for example, in regression models, when we want to make a better model, we try to play with our independent variables, like to make some changes in our independent variables to make a better model. Is it the same in this case for this model? Like changing?
Yes and no.
Okay.
It means that, and this is where it comes back to what I was saying, that well, if you, okay, let's say we've taken here, I've taken, how many variables was there? Like 20. 20 variables. Okay, I've taken 20 variables. If you add more variables that are not already in our model, the model might be better, because the variable that you add, you did not have in the first version of your model, might add something to explain the outcome variable. So if you add a variable that was not there previously, it will improve your model. It could or it could not improve your model, depending also on how correlated it is with the existing variable in your model. If it doesn't add much in explaining the variance of your outcome variable, then your variable is going to be only slightly better. Let's say you are modeling car ownership and you do not have income, you do a model without income, your model is going to give you, let's say, 60% chance, the accuracy is going to be 60% to predict that the household has one or more car or no car. But if you add income, we know that income is a very strong predictor of car ownership. If you add income, because it's a very important variable, it's gonna take more space in the variable relative influence, and it's going to increase your overall accuracy of your model. But if you add something that is completely irrelevant, it's not going to increase your model. If you simply remove some of those variables, you're not going to see a reduction. You're not going to see an improvement in your model. You cannot see an improvement in gradient boosting model by removing a variable.
What about turning a continuous variable, for example, into a categorical variable?
It's a good question. Again, I would say that if you have a continuous variable, you turn it into a categorical variable. From what for the tests that I've done, it's you're losing information. So since you're losing information, it's going to be not as good as the original continuous variable.
Thank you.
Because whenever you categorize, you're losing information. And as I said before, if you have a continuous variable, the algorithm is going to split continuous variable wherever it sees best to predict the outcome. If you split the category yourself, then it might not be optimal, and you're going to lose some information, so it's not going to be as good. So you better stick with your continuous variable. The reason we do that in regression is because regression assumes a linear relationship with our outcome variable. But what this allows us to see is that the relationship is not linear. It's not because you keep increasing the distance that the probability of walking is going to keep decreasing. There's a threshold effect. There's a nonlinear effect. We can see by the curve that there's a nonlinear effect. So if you were to include this variable in a regression, for example, you could say less than 10 or less than, let's see where it drops really, less than here, less than 5 kilometers, the probability of walking are high. Above 5 kilometers from downtown, the probability of walking and cycling are low. You can use a dummy variable in your regression model if you already know this kind of relationship. But here you're just best to keep it continuous, because you're going to be able to see this very more complex relationship than a strictly linear relationship.
Thank you very much.
Very good question, by the way. Very good question. It's you guys are thinking of questions that are just blowing my mind. Really, it's great. You're thinking of things that I didn't think was relevant to mention, but that are very relevant. And so you can create, back a bit to the coding, you can create this simply by a simple function like this, but it's very crude. It does not tell you, it doesn't give you many ways to refine and personalize your plot, but you can also extract the partial data, because this is based on something. This is based on the partial data that is extracted from the model. So you can extract that partial data yourself and then play with that data yourself. And when you extract it, there's a few parameters. Grid resolution here, I realize I do not explain it. Grid resolution, when you extract this data, is how many points should you take to extract that data. So this here, for example, is based on about 100 points. So it is the average. You can take less, you can take more, but up to a certain point. If you take more, but more than the number of observations, it's not useful. So it gives you kind of an idea of how you should use this. And so if you're familiar with a ggplot, it's similar to this. You add stuff and then you can customize your plot. And here you see I've added a title. I've added something here called the rug. So it gives you the decile of of your observation. So each line here at the very bottom, let me draw here. This is very useful. Each line here is a decile of your variable. So it means that 1/10 of our observation are below, that's about 4 kilometers here. 1/10 of our observation are below 10. It gives you kind of a sense of the distribution of your data. And here we see that between 20 and 30, there isn't very much. So it gives you how your predictor distributes in your observation. Very clear. I don't even know. Oh my God. Okay, we're coming. I'm like, I don't even have. There's so much left to be said. But we're coming 3 hours on this workshop. This is incredible.
I'll have to do a part two. But
But the code is going to be there.
Yeah.
We can do a part 2 if you want me to explain in detail, because I don't think we're going to have time to do the XGBoost models with the categorical variables. So let me just finish this. So here I've plotted another one, which is household median income. Also median income versus our outcome variable, which is the percentage of active travel within the within our model. Why is this so low? Yeah, okay, because this doesn't change based on that. Okay, so you can, for every variable you've included, you can produce this plot. You can also extract the, as I said, the partial data and look at this data yourself. But this is kind of a simulation of what happens, as I said, because this is the value obtained if you hold every other value constant at their means, and you use the model to obtain this value here of your outcome variable based on those values of the percentage of your predictor, holding every other variable constant at their means. Maybe I should have explained it this way earlier. It kind of makes sense. Yeah, that's what it is. You use the model to compute these values of your outcome variable, considering these values of your predictors that you're inspecting, controlling for every other predictors by fixing their values at their means. Yes, that's what it is. Okay, which brings us to, you can also do it by inspecting 2 variables at once. This allows you to understand the interactions between 2 predictors. Here, we can do it up to 3, but beyond 3, we don't have enough dimensions to really appreciate with our eyes the interactions. So here we can see that the colors indicates the probability of our outcome variable, not the probabilities, the values of our outcome variable. So the probability of the percentage of people walking to work, walking and cycling, based on the distance to downtown and the income, the average median income in our dissemination area. So you can kind of see the relationship between those 2 variables and their combined effect on your outcome variable, which is expressed by the colors. A lot of time and fun looking at those plots, trust me. So the idea of putting this here is that was not for us to interpret this. It was just that it's doable. You can do this, and it gives you more information. And I realized, oh, when we didn't do it in our papers, maybe we're going to do it if the reviewer asks for it. We'll see.
They'll ask for something that we haven't thought to do.
I don't know. I knew it existed, but I never looked into it. But it could be interesting to look at this, especially some of the variables we've included. But anyways, you can also kind of restrict this. What this does is that by a certain function, you're telling it, do not extrapolate. Only focus on a subsample that you're confident in your data. And it gives you this, which is kind of an extract of this, but without extrapolating on things you don't know about. Because there might not be values here.
Right, yeah, it's kind of
because very high income neighborhood, super close to downtown might not be existent. Same with like very rich neighborhoods, super far from downtown do not exist either. This is probably Westmount, by the way, this peak here. Okay, this I don't have time to go over, but it's going to be in the okay, which brings us to the one last thing I think you need to know is how do we tune are parameters. Now, for this very model, all those results that are presented, I've pretty much arbitrarily selected hyperparameters value based on what I knew, but you want to test this out. You want to know, okay, maybe I can improve my model by changing some of those hyperparameters. A general tuning strategy, and I'm taking this from a very informative book called Hands-on Machine Learning with R by those authors. Very good, because very good example on machine learning in general, including gradient boosting. They suggest this overall strategy, which is first, you're going to tune your learning rate, so your shrinkage. You're going to start high, and then you're going to go lower, and you're going to then determine the optimal number of trees based on your learning rate. Learning rate is the steps you take in the direction of the gradient. And then once you fix this, you can look at the tree parameters and tune learning rate to assess speed versus performance. It means that, okay, I have a super small values for learning rate, but it's taking me forever. If I put a higher value, it's taking me not as forever, but it's almost the same results. So at some point, you got to do some decisions there. And then you're going to fix the tree-specific parameters. The tree-specific parameters are the minimum observation in each node in your trees, and how many, they don't say it here, but the other point is how many splits are allowed in your trees. And finally, you're going to test those with cross-validation, blah, blah, blah. How do we do this in practice? Well, one way to do it is something called an hypergrid. In a way, we're going to run many models with a lot of variation of the parameters. So we're going to test all combinations of parameters that we test. And we're going to run models for each of those combinations and see which one produces the best results. So I give you the code on how to do that. Here I've tested only 36 variation of our model with different tuning parameter. For those 36 models, it took me on my 2015 computer 55 minutes to run this model. And it has only 4,000 observations. So it can be very long, especially with GBM, which is not as fast as XGBoost. But the idea is the same. You test out possible combination, and then you inspect. So we do this here, we test this, whatever, same model. Okay. And then we inspect how many trees did we need to reach the optimal number of trees, and what's the minimum root mean square error in the case of a continuous value that we reach. What we see here is that if you look at the first, and I've ordered the row based on the minimum root mean square error that we obtain with our model. That means the smallest value here, the better is our model. What we see is that you can see that shrinkage, interaction depth, number of and interaction depths are pretty much the same values. It means that these two should be selected because these two parameters, values for those two parameters, clearly are better than the others, because all the first and best models in our 36 model list that we tested have those values. After this, we can see that some values do not have as much influence. The minimum number of observation per nodes between 10 and 15, not much difference. Don't bother over it. The bag fraction, as you can see, 0.5, 0.5, 0.75. This is how stochastic our algorithm is. The closer to 1, the less stochastic. The closer to 0, the more stochastic, the more randomness you add in your model. It changes, but not as much. And it finally, it gives you the number of trees. If you see, we have some at 6,000 trees. It means that here we could actually rerun this and increase the number of trees, because considering that the shrinkage was lower, we didn't reach the minimum RMSE. We could even have a better model with these values if we increase the number of trees, but it's going to take us longer to run. So it gives you an idea of where to go with your parameter. Some parameters, as I said, have more influence than others. So you should focus, do not waste several hours of your time on this. Some variables are more, some hyperparameters are definitely more important than others, but some of them, like this one, do not change much, not much variation, at least in the values that I've tested. You can test other values, that's for sure. So in the end, you can run this kind of grid search several times by refining your values. Okay, it looks like it's between this and this values for shrinkage. Maybe I want to go deeper and see if there's values in between that could be better. So this is the way you should go about it. And optimally, you should do this optimizing on your final model with all your final variable to obtain the best prediction possible with your final model before inspecting the results with relative influence and partial dependence plots, and use the model for prediction as well. So that completes my example for the continuous variable. I don't think we're going to have time to do the categorical example with the XGBoost package, but I have the code. I'm going to finish and wrap it up for you. I'm going to add things that we've asked today, so it's easier for you to understand. Is there questions for now? Let me go back to this. I have the references here that I've put in the PowerPoint. I'm also going to share with all of you. And there's more that I even did not have time to include.
The start of a 3-month course. Yeah. Go ahead, Bruce. Yeah.
This was ambitious for 3 hours, Owen. That's what
Yeah.
Well, first of all, I really want to thank Jérôme. Honestly, that was, I can say, one of the best or the best workshop I have ever attended in my life, really. So I'm going to ask my questions. Well, I remember you mentioned that comparing predicted value and like the real value of our outcome, I guess.
Yes.
So is it for identifying the accuracy of our model?
Yes. So
and if the dependent variable is categorical, so the method for like identifying the accuracy would be completely different?
No, it's similar. I didn't get to it, but I'll explain it. It's a very good question. So I do the same process with the categorical variable. It means I use a 70% training set. You can choose other values as well, but 70-30 is kind of typical. You hold out that 30%, use that 70% to train your model. And then once you train your model, cross-validate your model using the internal cross-validation process. And then you can even hypertune, tune your hyperparameters, and then you check the accuracy of your model. In a categorical model, what we're checking with this accuracy, with this prediction, is how good is our model. And so we're going to predict. What it's going to do is that it's going to give you a probability of the outcome. So let's say we have a binomial outcome variable to not or not to own vehicles in your household. Very simple. The probability is going to be between 0 and 1, and you can set that at 50%, the probability is that you're going to have a car in your household. Below 50%, you're not going to have a car in your household. So this is what we're doing. We're using your test set. We're using the model to predict the probability on our test set. And when using this probability, we use a simple threshold cutoff of 0.5. We say if the probability of having a car is above 50%, then this observation will have a car. And then, so we do this for all observation in our test set, and then we compare. We compare the prediction of the model with the real outcome of the model, and then we can see how many did we get right. So it gives you a percentage that we got right. For example, here in this model, this binomial model, the final accuracy of my model of predicting car ownership for one adult household with only one adult that can drive a car, is 71%. And we have an error rate of 1 minus that, so 28.9%.
Is there a specific value for that, or just we can interpret like the higher it is, the better the model is?
Well, if you had a model that is 50%, it means your model, especially for binomial outcomes, if your model is 50% or less, it means if it's 50%, it means that your model is not better than random guessing. If it's less than 50%, there's something wrong in your model because it's not good at all. It's worse than random guessing. So the closest to 100% is the best, of course. The lowest that you're gonna go is 50%. Really, your model is not gonna produce something below 50%, I think. So 71% is 21% above the 50% threshold of random guessing.
And another question is that if, for example, we use a simple decision tree and we say
Yes.
that it's like that was not a good model. Do you think like using this model can like, I don't know, like will give us a remarkably higher accuracy? It will like change, I don't know, like the results, or I don't know. What do you think about that?
You're asking me, can we compare this value with a single decision tree?
Yes.
Yes,
Like
you could probably, yes, you could probably run this. I must admit, I don't have the code for this, but there are ways to do regression trees in R, and you can do the same thing, build a single regression tree with the same variable and see what result it would give you, because a regression tree is going to give you the same. You will be able to use your prediction tree to predict your value. You can use even the same test set and see, is our regression tree better than this boosting method? I did not test, but the literature is clear on that. This method should be better than the one regression tree. But it is something we could test. Now that you make me think of it, it is actually something that I want to test to see how much better it is. So yeah, it could give you a benchmark. If I use one decision tree, maybe I'm going to get 65%. I use this boosting method, I get 71%. So it's much better.
Yeah, okay, thank you very much. And like, I think the last question, what are the, like, among all these plots that you presented, what are the final results that we have to, for example, put in our paper or in our thesis?
Well, the relative influence are one of the results here. This is something that I've done with like very nice graphs. Let's say here, this is a plot that we've included in our model, in our paper, for example. Similar to this, it shows the relative influence of all the variables we've used in our model. So it tells us which variables are not very important, which variables are important. So this could be a result that you put in your model, in your paper, sorry, the relative influence. Those here, for example, this one, how much is this is not necessary unless you were doing a methodological paper on gradient boosting, but I don't think this is necessary. You can just express this that like you've reached optimal number of iteration after this amount. We don't see any improvement after that many iteration. This is how we selected the hyperparameters and so on. But the results you want to present are relevant influence and of course those partial dependence plots, because this is what we're interested in, because this is what shows the relationship between our predictors and our outcome variable in our model. And then you select which one you want to show. Here's an example. In XGBoost, you cannot include categorical variable as is. You have to convert them to values, to numerical values. So if it's a binomial predictor, you're going to have two values, 0 and 1. So this is what the partial dependence plot is going to look like. Incapacité ménage, it means, is there someone with limited mobility in the household? If the answer is yes, we see that the probability of having one car for one adult household, it means that it's probably the person with disability, is much less than if there's no one with the with mobility in the household. So it shows us the influence, the direction of the influence of a categorical binomial variable. We also have something here. Number of people that are 17 less in the household. It's discrete. It's not very continuous. It's either 1, 0, 1, or 2 in the case of one adult household. So you can see how having more children for also with one adult increases the probability of having a cough. But this could also be categorical in a way, but it's just that you have to put it numerically in XGBoost to be able to produce those plots, but that's why they're this shape, because there's no in-between values. While continuous variable is going to give you something like this. Good. Other questions?
Thank you. Yeah, just one more. Just let's just imagine if like the accuracy okay, I don't like 50% or less than 50% as you mentioned. Should we change our model completely, like switch to another, I don't know, method, algorithm, or there are some ways to improve the model?
Good. Okay, good question. If you're slightly above 50% with the variables that you've included, you can probably improve your model a little bit with tuning the hyperparameters. That's the grid search that I did here. You can change a bit the accuracy of your model by changing those hyperparameters. But there's a limit to this. If your explanatory variables are useless, they're not related at all to your outcome variable, it doesn't matter how much you tune your model, you're still not going to get a good model. So if you start with a very terrible accuracy rate for your model, you might ask yourself, do I have the correct predictors in my model, or are there other explanatory variables that I do not have included that I should include before starting to tune your model? Because tuning your model is time consuming. Like, as I said, running this hypergrid search of like testing 30 or even more. I've tested for a paper that we did, the last paper we did with Owen, I've tested like 350 models. It ran overnight. I didn't want to do this 10 times. So I did this on the final model with the final variables that we're going to use in our model. So you better select your variable first and then try to fine tune your model using the hyperparameter.
Thank you very much. Perfect. Thank you very much.
Any other questions? I don't even know how many people are still listening. I know Bob.
Yeah, long has a question. Also, yeah. I don't know if people if people can stay, or I'll just mention. I'll talk with Jérôme, but one of the things that we had talked about was that now that Jérôme has given you a couple of examples, you can try to run like a model yourself, and then I think Jérôme is kind of open to responding to some questions, and then I'll kind of pay him as a TA on that. It's like I have some research funds that need to be used, so I'm happy to help. I'm happy to help students where it's like if there's some kind of exchange, not just free money, but and then we'll talk about maybe having another session where maybe it might be more of a kind of general problem shooting session. So
I think that's a good idea. Yeah, I think it would not force people, but encourage people to look into this very quickly in the next few days. If we say like, oh, we're gonna have a session next week or the week after that, and so be prepared to have your question. Be prepared with all your questions for the next session. Personally, I know I would kick my butt to test out things if that was the case. So I think it's a good idea, Owen.
Yeah.
If
so
we'll
check. Yeah. So maybe it works again on a Tuesday afternoon in a couple of weeks. But I'll let Long, you had a question. Go ahead.
Sorry, I just switched my earphone because AirPods is out of power.
Oh no.
I just have one question, because first we should define or assume the relationship between our maybe explanatory variables and our dependent variable. And after that, we found a non-linear relationship between the variable and the dependent variable. I'm not sure if we change the relationship because we assume that it's linear relationship.
I'm not sure to understand your question.
I think
Yeah,
so.
because yeah, first we define the relationship, the function, and
Do not
then
define
we
it.
yeah
The model, this is produced by the model.
okay, because first we have that tilde because we define there.
Which
In
one?
the okay, so I think yeah, so in the
In the
what is it?
beginning,
Here?
Yeah.
This distance, this relationship between distance to
No.
downtown. No?
What was
The-
the term that you used? So before that, like you said, okay, depending on the, like the type of dependent variable, there were certain
Oh, yeah,
different,
okay, yeah. Yeah, okay.
like
Okay,
you
I
had the
see what you're
Gaussian,
talking
or you
about.
had the
Okay, yeah.
Yeah.
Which loss function should
loss
you
function.
use?
There we go, loss function. yes.
Depending on, let me see. Okay, here.
yes,
This is the function, not the red. The red would be a normal distribution.
yeah,
Behind is the histogram of our outcome variable we are predicting. As you can see, it is not normal. It is skewed with a long tail.
good, yes,
So does this mean we should use specific loss function for this? I think so. The answer is most of the modeling that I've done was with categorical variables. So I have not investigated continuous variable as much, but I do think that if we go back and I'm going to look into it, into the references in the literature on this, depending on the shape of that, we might want to select one loss function over the other.
But then
So the answer is yes.
long was your kind of follow-on question was saying if, like, I guess like the Gaussian is assuming like kind of a distribution, but then I don't think it, for the independent variable, what's interesting about this approach is you don't assume for the independent variables relationship with the dependent that it's like a linear relationship. You actually see with the PDPs, you see it's like, oh, okay, this is, yeah, so some of the stuff that Jerome produced, it's like, oh, okay, this is a pretty linear relationship, but other ones it's like, oh, it plummets, right? There's like a
yes,
yeah, so I mean that's interesting because like in the traditional methods we do often assume like, oh, we're assuming a linear relationship. That's
yes,
not necessarily the case, which is what is really, I mean, for me was really interesting with this, because you get to a certain point where like, oh, after 5 kilometers, the distance maybe to the center of the city doesn't matter anymore or something, depending.
yes,
Yeah. So it was
Okay.
like, right, so it's a steep linear relationship right up to 10, but in a traditional model we might end up assuming, right, like a different relationship. So
Yeah, so the loss
Yes.
function that you select for your model algorithm, it has nothing to do with the predictor.
Okay.
You indeed, and I should read more on this. It could be you can choose different
Yes.
loss
Just here.
function. I'm looking for it. Yeah, loss function depending on your outcome variable you're trying to predict, but it is not no relation at all to your predictors. Do not base your loss function on your predictors.
Okay. Okay. Thank you, Cheryl.
Bobin raised
Sorry,
a hand.
just two small questions. So for first one, just now you said you combine the sampling method with cross validation. So I didn't find the code for the sampling to fit the overfit.
Wait, what's your?
You just said you applied both the sampling method with
Yes.
the.
Okay. Yeah. Okay. Here, let me show you here. So here is the code for first splitting the original data set into a training set of 70% and a testing set of 30%. And then we use here, I use DA, dissemination area train, and dissemination area test. We use dissemination area train in our model, which is here, data. Here you see I use DA train. Where does the cross validation comes in? It's here, CV folds. You see, That's why I said it's internal validation. If you were to put 1 here, it means there is no cross-validation.
Yeah, this is cross-validation. I know that, but where is the stop sampling?
Where is the stop sampling?
Subsampling, I think.
Subsampling.
So with the
It
with your
happens
Ks.
internally. Here, let me see. Let me show you a.
But where? So did you define the number of Ks? Because you gave the example. You were saying, oh, like here's an example of 3, but maybe you'd use 5 for the train, like the training data. How does that? How do you say how many? Yeah, like the training data. The K, is that what it is? The CV folds.
CV fold is the number of is the number of split in your training data. So a CV fold of 5 means that
you split the training data into 5 subsamples.
And at every iteration, you take 4 out of those 5 randomly, 4 of those 5 subset, and you use them for training your tree, and you test your new tree that you've added, or your entire ensemble with this new tree with the final 5th subsample that has been left out.
Yeah, I know the cross validation. Yeah, I mean the method subsampling. You said you have to divide the samples by column or divide the samples by volume.
Yes. Okay.
So you
the
said you combine these two methods.
Here, this is where it happens. This is the bag fraction. The bag fraction in GBM, with the GBM package, you can only split your sample by observations. So not only does it split your thing in 5 and it takes 4/5, but it also takes only half, because I've said 4.5 of those 4/5 every time, in a random random sample of those 4/5 every time. There's kind of a lot of sampling here, but so that's where it is. This bag fraction. It splits fraction of rows subsample is the bag fraction, and the fraction of columns to subsample is not. This is a parameter that is not available in the GBM package. You have to go to XGBoost to have that, and in XGBoost you have something called, let me see where it is, parameters. You have something called column sample by tree. 0.8. So here I take 80% of my columns or 80% of my variable at every iteration.
Oh, okay. So
that's where it is. Sorry, I didn't understand your question at first.
Yeah. So 80% for the 80. So you only select 80% of the variables
at every iteration.
And
but this 80% is random.
For in each iteration.
Each tree or iterations that you add, it's a random 80% of your variables. So if you have 10 variables, it takes 8 out of those 10 to build a tree. It leaves out 2. But the next tree, it could take 8 others among those 10. So it's not going to be always the same 8. That's what it means.
That's probably like one of the reasons it's good with multicollinearity, I would imagine.
Exactly. This is why it kind of it helps.
The robustness of it is
the robustness. Any randomness that you add usually helps the robustness of your model.
And you also have the volume, the rows sample, right? The sub rows, subsample by rows. This is for column.
Oh, the sub. The
subsample by row here is just called subsample. So subsample in XGBoost is the same as what is called bag fraction in. I know they use different things.
Subsample seems easier than bag fraction.
I should include a. I think I'm going to include a table. I think I'll have to rewatch this whole
like a dictionary.
To take notes. I'm going to add a table of like okay, this is the hyperparameter. This is how it's called in GBM. This is how it's called in XGBoost. This is what it does.
Okay.
So it's subsample here and column by tree, and there's this final one which is I did not include it here, but you can also it wasn't my PowerPoint, I think.
Yeah, the one you
The
said that
final
you were
one
less.
that I've not really tested,
Yeah,
the
yeah,
fraction
yeah.
of columns to subsample before each split in each tree.
Okay, each tree.
So normally you only this fraction of columns to subsample is before creating it's before each iteration, but you can also decide to subsample columns even before you do a split in a tree. But it's adding randomness over randomness over randomness. At some point, I don't know how useful that is, to be honest.
And just now you also showed the bag function something which equals to 0.5. So what that mean?
That was in the GBM.
GBM, the bag
Yeah,
fraction
the bag
is
fraction.
it's the fraction of rows to subsample at every iteration.
Oh, so this is the row something.
This is a row subsample. There's no column subsample in GBM.
Oh, okay.
In
Okay.
XGBoost, you can have row subsample and column subsample.
Okay.
And I think there's also the option for the third one that I've explained here. This fraction of column subsample, not before each tree, but before each split. But to be honest, I have not tested it. But it's there. The function is there. You can
for each split.
Yeah.
Wow, it's a lot.
Yeah, and it gets hard to explain.
Okay, and
so that's why we're saying that there's a lot of flexibility. You can.
Okay, and another question is very simple. The RMSE. So it is
the
the
root mean
larger
square.
the better.
Yeah.
Is the larger the better or the less the better?
I think it's
the
smaller.
less the better.
Yeah.
The smaller the root mean square error is the mean. Let's say you have a value. Let's say your real value is 5, and your model guessed that the value is 7. So the root mean square error is going to be
4.
7 minus 2 minus 5. It's 2. Squared 4 root 2. So it's 2. But you average this over all your observations. And why root means square? Because minus and positive, you want them to be.
Oh yes.
Yeah. So that's why when you show the result, I find you only analyzing the first one. The first one is the biggest value, right?
Oh yeah, because at first, this where is it? Here. No. This.
No, a table.
No. I think
when you do the parameter tuning.
I think it was the smallest. I think he'd
ordered. Oh yeah,
them.
sorry, the parameter tuning. Okay, this here, min RMSE. This is the final value here. That's okay. Here, you see that blue line? It gives us an RMSE of whatever 0.0. No, this is not. This is squared error. This is not loss. This is not the RMSE, but you can just compute it. This is this for every model that I've tested in our grid search. So you see for this very specific combination of parameters, of hyperparameters, we reach optimal number of trees at about 3,000. It gives us a certain RMSE. If we test other hyperparameter combination, you might reach something that is lower. If you reach an RMSE that is lower, it means your model with those parameters will be better. So higher in the table, it means those models here are better than the one at the very bottom here. So here you see the RMSE is 0.06, and here it's 0.05.
Okay. So lower the better.
So lower is the better. So you order them by lowest to highest, and it gives you what hyperparameters are better.
Yeah. That makes sense. And maybe I don't know, because I cannot understand why you generate maybe 100 or 1,000 trees. Why and combine all of them? So that is the meaning of boosting.
Yeah, that's the basic of boosting.
So for each tree, you use maybe subsampling, cross validation, and then have yeah, so this tree, you after that one, then you generate another tree, and then you generate another tree. So why you generate so many trees instead find only one best tree?
It's not one best tree. At the end, you take all the trees to indeed, you take your final iteration, but your final iteration is not one tree. It's all of the trees together.
Yeah, okay.
You don't take the final tree. You take all the trees up to this final trees. The model uses all the trees up to this final tree to make your prediction. It does not only use the final tree.
Yeah, your final parameter means, for example, you select 100 trees to get the final result prediction, right? So it's not only one, so it's 100 trees.
Exactly.
Yeah, so for these 100 trees, you cannot analyze the results for the prediction, right? Because it's difficult. Each tree have a parameter or something variable or estimators, right? So you need to combine them together to use the importance or influence to analyze.
That's why we sum over all trees, because if you take only one tree, it's going to give you the relative influence of that variable for that single tree. But in the entire ensemble of trees that we have, it might be different. So that's why we average over the entire number of trees that we have. And this is how we compute the relative influence of our model.
Okay, but for the 100 trees, maybe you give some constraints. For example, the number of tree dice and the number of something. So maybe it's not a completed difference. There's some similarities between these 100 trees, right?
Oh yes, for sure.
So it's not randomly generated the trees. So
no, it's not random. I mean, there is some randomness added through the different hyperparameters, but those trees are not random. They are based on what have we learned so far with the model, based on the variables that we have. Can we split the variables differently? Can we organize them differently so that we get a better result? That's what the new tree that you add to your ensemble does. It learns, okay, it looks like this tree, up to this point, these observations were very hard to predict. How can we split the trees differently with the variables that we have on the hand to try to improve the prediction of the entire ensemble up to this point?
Okay, so when generating the trees is based on the algorithm, right? It's not, so I mean that when generate the tree, so the algorithm generated automatically, but not we selected by certain rules. For example, for this split, we use the number of age, the age. For this split, we use the number of vehicles.
We don't do it manually, no.
Yeah, I mean that the position and the variables was decided by the algorithm.
Yes.
Right. Okay, so they just choose the variables and then generate 100 trees and then calculate the importance and influence, tell us the results. Okay.
That is why, and because each tree is different, technically, you could extract, I don't even know if it's possible, but you could theoretically extract all the 100 trees in your model and look at all those individual trees. Okay, here in this first tree, we've used these variables and they were split this way. The second tree used those variables that were split that way, and so on and so on. But looking at 100 trees or looking at 1,000 trees, it's just not possible. I mean, you cannot do that.
Okay.
So the algorithm does it for you. It chooses what tree, how to split your variable, which variable to select with some randomness, but still to optimize your algorithm, to optimize your loss function. If the new tree that you've produced is better, is improving the overall accuracy of your model, then this tree is added to your ensemble of trees.
Okay. So the loss function is standardized to choose a tree.
Yes.
Okay. Thank you so much. Yeah, thank you. It's very interesting. And it's a new concept for me because I only fell into the traditional decision tree method. And the forest concept, it's very new for me. Thank you so much.
You're welcome. I understand it's not easy to grasp how this is done, this addition of trees, but hopefully I've demystified it a little bit. And you'll be able to keep reading further. Maybe you're someone who sees the equations and you'll understand right away how it's done. I'm not like that, but anyway, so you'll, with all the references I'll send to you, maybe some people will explain it in different ways that I've done it and you'll understand better. But now at least you have a good understanding of how it works conceptually.
Share some references to us and then we can learn more about it. Thank you so much.
I'm gonna have to go, and I think probably, I don't know.
Yeah, me too.
So thank you, Jérôme. I think everyone, I mean, the direct feedback was very positive. And I think, as I said, so once it'll take some time for my computer to process the 3.5 hours or so of recording. And then I'll figure out the best way to do it. Sometimes I can put it on a private thing on YouTube. It just like would take less space than me storing it on Dropbox, but I'll see what works.
Private thing where people need a specific link.
They need a specific link.
Find it by researching.
Exactly.
That could work.
Have it on the searching option.
And we have to find a way as well to like the best way to share.
Because because I think if it's on YouTube as well, like, because then you'd stream, as opposed to if I put it on Dropbox, it's like the actual massive, like whatever, how many gigabytes of space for the video. So I'll just check exactly how that works to put it up on YouTube. But
it's not super complicated. I've done it before.
I've put up my the course material when we first went into COVID on there. And then Poly developed their own internal system, and I don't know if I can use the internal system, like the Poly video one, but then anyways, we'll find something to allow it for others to see.
And for the rest of the material, I do think that Teams might be the best way to share it. I'll see where I can put it on Teams. And for those who are not on Teams, Bobin, I don't know, I think you're still on the Polytechnic Teams.
I can open the Teams.
Okay, perfect.
Please add me into your groups. Then I can see them.
I think I can create the group, or I'll find the best way to do it.
You can send me invited by my new email address. I think I can also join the Teams.
That's good.
Okay.
I think creating a group could be interesting because it could allow me to answer all the questions at the same spot. So if people
I think that's probably
put them there. So that could be good. And then maybe the best way would be to send another doodle, or just set the same
same time. I think it's probably easiest maybe if we said 2 weeks on the same Tuesday or something, same time on a Tuesday. But
but again, it would mean that the people who were not allowed to join now would not be allowed to join. Maybe I can send a doodle to everyone that manifested its interest, even though they could not necessarily attend. So some people might watch the recording and then have questions.